Un, deux. Hello, Jean-Pierrot. How are you? Jean-Pierrot, do you hear me? Bon, lui, il a l'habitude, hein, il fera son partage d'écran plus tard. Hein. Ok. Tac, tac, tac. Il en manque un. Ok. Alors là, je vais demander à ceux qui font l'introduction d'arriver. Je lui explique comment marche le micro. C'est parti. That's the next.
Ok. Là, il a petit fin. Alors, le slide. Allez. Le laser, on ne le voit pas à distance. Elle est revenue en arrière, du coup, ça fait le bordel. Je repartage l'écran, en fait, c'est revenu en arrière, ça a arrêté le diaporama. Ça arrête tout le carré, ça arrête le partage d'écran en plus.
Ah d'accord.
Et là, donc. 1, 2, 1, 2. Donc, soit tu le mets sur ta chemise, soit tu le tiens comme ça.
Ok. Tu m'entends là?
Je pense qu'il vaut mieux qu'elle le tienne parce que c'est.
Vaut mieux que je le tienne comme ça?
Mieux, ouais.
On l'entend mieux si je fais ça?
Ouais.
Dans l'autre sens? Comme ça?
Ouais, avec la partie avec les LED vers soi, ouais, les deux LED vers soi.
Le violet vers moi?
Ouais.
Comme ça? Comme ça?
Ouais.
Vraiment proche alors.
Mais celui-là, il marche mieux. Hein.
Alors celui-là.
Ok.
On va prendre celui-là. Ça, t'en as pas besoin. 1, 2. Donc ça, on peut le couper.
Allô?
Après, il faut
Do you hear me well? In the other room, do you hear me well too? Make a little sign. Oh, hello.
Donc on est bon.
So please take a seat. We will soon start in 1 minute.
Donc, ce que je vais faire, là, je vais couper le son d'ici. Ouais. You can.
Welcome to this Ocean Reanalysis workshop of the Copernicus Marine Service. So we will be starting very soon. We will be giving some introduction together with Chonchue and Romain. We are very happy to welcome people here in person and welcome people online. We hope we're going to have an interesting workshop. So it's our first workshop in a workshop. So I hope you are sitting comfortably. This is a very nice place in downtown Toulouse. So we will be ready for very fruitful discussions. And thank you, everybody, for being here. And thank you for people online for listening to us for these 2 days. Okay, so it's not changing. Oh, yes. So we have organized a Slido. So it's a website, slido.com. You go there and you enter the code 3628533. And this way you can connect to the workshop and you will be able to ask questions if you are online or if you are in the room. Of course, if you are in the room, you can ask questions directly. But you can use also this application to ask questions. And you will see that for each session, we have prepared a little survey, a very quick one. It's going to take you 5 minutes to answer some questions, to give us your feedback if you are here or if you are online. So we will gather this feedback and we will use them during discussion sessions and roundtables. So thank you for connecting to Slido and participate in the workshop using this tool. Okay, so it's, yes. So this is what it looks like. So you have questions and answers on the left and the polls on the right. So you have 2 different tags and you can go from one to the other. And in the polls, you will find a poll for today. So as I said, if time permits, we'll take questions from the room as well. But of course, we will be very strict with time so that people online don't get too bored. And also for us to have more time for discussions during the coffee breaks and discussion sessions. If there are questions online that are not answered during the workshop, we will answer them afterwards and send to the registered participants who will send the answer to the questions. We will select questions and use the results from the poll during the roundtables and discussion sessions. So that's what I needed to say. Yeah, if you want to go on Slido using your phone, it's perfectly possible using the QR code, but you can also use Slido on your laptop in a web browser. It's working as well. Okay. So I'm getting used to changing slides, so I'm a little bit ahead of time. Do you want to say something, Ronan and Junta, apart from... do you want to say welcome? Yeah. They are very happy. They are smiling. You can't see them. But yeah. Yeah, we really appreciate that you came, all of you, to be able to discuss together. So thank you very much again.
Yeah, we thank you so much because we really have people from far, long way, long trip to come, and thank you so much. And we have 2 rooms here. You can also, how to say, back and forth. Yeah. Also, the coffee break we have downstairs. The coffee break will be downstairs, and so you will be able to see the posters. Some of the posters are here in this room or in the other room on the first floor, but you can go downstairs and see some posters downstairs and go to the coffee break. Okay, and dinner? And the dinner, maybe I'll display it later on. Yeah, because people online may not be so interested, but well, people online, you miss a dinner. There was something I wanted to say. Yeah, of course. Thank you, Vincent, because Vincent has been organizing all the practical details and not only. He's been printing the posters and everything. So thank you very much. Well, thank you again at many times during this workshop. The online questions only from the Slido. Yeah. If you are using the Zoom, if you are online, you are using the Zoom, you will not be able to ask questions in the Zoom. You will have to go on the Slido. And the Slido link is also shared in the Zoom chat. So if you don't remember what it is, you can find it again in the Zoom chat. And Vincent will post it from time to time so that people are reminded that they can ask questions on Slido. Okay. So I think now we are ready to start the first presentation, which is me. How convenient. So I'm Marie DREVILLON, by the way, working at Mercator Ocean, and I'm very happy to introduce Marine Service, the Copernicus Marine Service Reanalyses and multi-year products to start this workshop. And so I will talk about the blue, green, and white ocean multi-year products that we deliver and their evaluation framework, and how we describe the strengths and weaknesses of the products, and also say a few words about the need for regular international intercomparison exercises. So the ocean for the Marine Service is a blue, so the physical ocean, temperature, salinity, and currents, the white ocean, the sea ice variables, and the green ocean, biogeochemical and biology variables. And so the Copernicus Marine Service brings together satellite in situ observations and 3D models to describe essential ocean variables. And the data are verified. We compute indicators, we do reports and training sessions, and have a lot of users worldwide, which is well known now. So how is it organized? We have global and regional products. The global area here, and what you see is the regional products are focused on the European seas. There are 7 different areas, and usually the regional products have specificities. Either the algorithms or maybe the models are different. They take into account more processes, or they have higher resolution. So the catalog includes observations, as I said, in situ and satellites that are also assimilated by numerical models using data assimilation. And all of these are used to produce blue ocean, white ocean, and green ocean variables. And there are several types of time series. We have multi-year, what we call multi-year, reanalyses and reprocessed observations. They span from 10 to 45 years. We have real-time products, analyses, or observations that are available 2 years before real time, and of course forecasts from 2 to 10-day forecasts, all at the same place. So this is, for information, the list of variables we have for the blue ocean, the green ocean, and white ocean. Of course, temperature and salinity and currents for the blue ocean, also sea surface waves, sea level, and wind. For the green ocean, the plankton, but also the nekton, which is the next trophic level. And then you have the carbon variables, nutrients, optical variables. For the sea ice, the concentration, extent, thickness, velocity, the surface temperature, and the snow. So all these observational and model products on a marine data store, but also they are delivered together with description of each product. There is a product user manual, and there is also a quality information document. And of course, the service desk is very important to explain how to use the product and also answer the questions and direct the users towards experts to answer their questions. Of course, there's an extensive use of Sentinel data and contributing missions too. So one of the motivations to produce a long time series of the past is the Ocean State Report, which is an important asset of the service. It's the driver of the ocean reporting activity within the Marine Service. There have been 7 issues until now. The 7th one has just been published in State of the Planet. It's a collaboration between more than 150 experts among more than 25 European institutions. Yes, okay. And so to produce this knowledge transfer of science-based information for the physics, the biogeochemistry, and the biodiversity to downstream applications and a more general audience, the experts use the reprocessing of ocean observations and also reanalyses together, combined sometimes, or sometimes one or sometimes the other, to compute ocean monitoring indicators and also expert assessment in the form of peer-reviewed articles within this report. There is also a summary for policymakers, and it's important for it's an important information for decision makers, environmental agencies, or stakeholders for sustainable development, and of course the general public. And so this is one of the strong motivations for producing long time series that are able to capture the variability and the trends in the ocean state. So first, the thematic assembly center really play an important role in gathering the information, the observational information within the service and preparing this information by aggregating in situ observations and quality controlling them, and also processing the satellite information into L3 and L4 products, which are then assimilated to produce ocean reanalyses by the monitoring and forecasting centers. If we focus now on these specific products, model products with data assimilation from the monitoring and forecasting centers, here I've put some numbers of the number of products for the physical ocean, the white ocean, the sea ice, and the green ocean, the biogeochemistry for the forecast, the multi-year. So here is the number of ocean reanalyses that are disseminated by the Marine Service, and ocean indicators that are produced too. So what you see is that there are 12 blue ocean reanalyses, 4 sea ice, and 6 for the biogeochemistry. So the blue variables, we have much more products for the blue variables today. And one also interesting fact is that since 2016, the number of users has been constantly growing for forecast products, but also for multi-year products, so reanalyses, and even faster, the growth of the number of users is even faster for reanalyses. So there's a real use, these time series are really used by the Copernicus Marine Service users, and they are also used together with the forecasting products. And they are sometimes necessary to calibrate the real-time applications in some way, or they are necessary as a reference, for instance, to detect extremes in the real-time applications. So there are several motivations for doing this reanalysis. Okay. Not switching. Sorry. Where do I have to point? Or it's good. Thank you. So on this schematic, I'm showing that how much the observation network is constraining us in the production of reprocessing time series and reanalyses of the past. So we have, for instance, reprocessed ocean color observations from satellite are available since the late 90s. Then satellite altimetry for sea level and waves are available since 92, 93. And then satellite sea surface temperature and sea ice is available since the 80s. In situ observations in the Marine Service start in the 1950s. And so from this, in the Copernicus Marine Service today, we produce reanalyses mostly for the altimetric era, starting in 1993. Because we are able, from the altimetry and the rest of the observation network, to derive time series that will have realistic mesoscale features, let's say, and interannual variability. So this is the first choice that we have made. And now we are starting to think about longer time series using the in-situ network, and also using maybe the shorter time series that we have that are produced using our near real-time systems and are really starting. Oh, sorry, there's an echo here. I can hear myself. Okay. So I will switch. You don't like this slide? Okay. I will try to switch. Okay. So for the reanalyses that we are doing, so what we try to produce is homogeneous and continuous and high quality description of the past. By homogeneous, we mean that in principle, we don't change the production system that we use to produce this time series. We don't change it in time. We use the same system to produce the full time series. It is continuous, it has no gaps. And high quality, it's because we use the best input possible. We use the high quality inputs reprocessed and quality controlled. And we also use atmospheric reanalyses to force the ocean reanalyses. And so what we are trying to develop is to have maybe 2 lines of products. So the current line of product with spanning the satellite observations era, and a longer time series spanning the in situ era. But for all these lines of products, try to update them frequently, like every month, to produce time extension that goes up to, let's say, 1 month before present, which is feasible today using ERA 5T forcing, atmospheric forcing, which goes up to 1 month before present. So this is already done by some of the regional products, and the global GLORIS 12 reanalysis will soon be updated this way in the service. So this is let's have a look at what are the results of the reanalysis. So I will start with the global ocean reanalysis. This comes from the Global Monitoring and Forecasting Center, and what you see here are root mean square differences in the observation space for the temperature here in the first 2,000 meters and for the salinity in the bottom plot. And what I wanted to illustrate here is the influence that the in situ observation network has on the results. And what you see is the difference between the period before Argo and the period after Argo is beginning to take measurements after 2004. So you see there's a drastic change in the statistics that we get in the differences with respect to available observations that nearly are twice smaller than they were before Argo. So there's a larger uncertainty in the reanalysis before Argo comes into the picture. And so this is this results in the fact that, for instance, in the Earth heat inventory, here a paper from Karina von Schuckmann, what they use, the reanalysis that they use, it's only the reanalysis starting in 2005, and they are not using the period before because there is a large uncertainty, large spread in between the solutions. So there are still, we still need to further assess regional and global warming in ocean reanalysis for the period pre-Argo. So we still have work to do on this specific topic. So what you see on the right is the use of several reanalysis products together with observation reconstruction heat content to evaluate how the heat content trend has increased within several decades. So this is the heat content trend over the last decades. So now I will give you an example of regional reanalyses that are delivered. So here in the Mediterranean Monitoring and Forecasting Center, this is the wave reanalysis, for instance. And here we see that we get closer to coastal users and closer to coastal areas. In particular, these reanalyses are validated against buoys that are quite close to the coast. And these reanalyses are also limited by the number of observational references that we have, but they give quite good results at the interannual and seasonal scale, and also give quite good results for extremes and trends, even if some of the extreme waves are not captured. This is something we will go back to in the workshop. Regarding green ocean reanalyses, what I wanted to illustrate to start this workshop is the number of observations that are available as in situ observations available for green ocean reanalyses. We have ocean color, remind you, starting in the late 90s, but then the in situ network is very sparse compared to the physical in situ network. So these are bio-Argo floats on the left. And on the right, these are the Copepod database observations that are available for the zooplankton validation. So you can see that the data are very sparse, but still we can do some evaluation using this data. Now, regarding green ocean reanalyses, another challenge for us in the future will be to capture the trends in a ocean carbon sink. And if we look at these trends today in the products we have for the global, we have a trend that is probably overestimated compared to the ocean global carbon budget. So we are in the process of developing the assimilation of carbonate variables in green ocean reanalysis to try to improve this. Now the white ocean reanalysis. This is an example coming from the Arctic Ocean Monitoring and Forecasting Center. What you see is a difference in sea ice thickness for the winter season, and here October, November, and here February, March. And you can see the difference in sea ice thickness with satellite with respect to satellite data, and here with respect to in situ data. So it's working quite well actually, but there are still biases, in particular in the Beaufort gyre, which is a typical bias in Arctic sea ice reanalysis. And I don't show the result here, but the sea ice extent variability is well captured in these reanalyses. But we have challenges for the sea ice volume and the thickness. So now a few words about intercomparison exercises. So there have been intercomparison exercises in the past, such as ORA-IP, the Ocean Reanalysis Intercomparison Project from Godet, Ocean Predict, Cliver GSOP, and also the cost action that followed, which was called Evaluation of Ocean Synthesis. And from these were very useful, as they allowed us to really derive which variables were robust, were working well in all different reanalyses, and to identify which were the remaining challenges and uncertainties left. And also we have been intercomparing on a regular basis. Some of the reanalyses are compared regularly in the tropics by multi-ORA by the NOAA. Also, we have the multi-product GREP that will be explained later on in the workshop. And the multi-product approach that is used in the Ocean State Report is another example of intercomparison that has been useful. So this is an example from Andreas Torto's paper in 2017, a comparison in the sea level, global sea level and regional sea level, which shows a good consistency between the ocean reanalysis products. Actually, it's working quite well. All these reanalyses usually assimilate sea level anomalies. And the ensemble of reanalyses actually gives better results. If you use them as an ensemble, you obtain better results than objective analyses, especially in the Southern Ocean. But there are still large uncertainties remaining for the long-term trends. And this other example is for the Atlantic Meridional Overturning Cell. And what I wanted to show here, that this is the most recent paper we have on the Atlantic Meridional Overturning Cell intercomparison. And this paper has shown that more recent versions of the reanalysis were obtaining better results with respect to the previous paper. So there is a continuous improvement, and we really need to go on doing these intercomparison exercises because the products evolve, and we need to redo this intercomparison to really capture what has evolved and what is better represented, etc. So no need to say that I advocate for a new intercomparison exercise that we will talk about later. So as a conclusion, I would say that these multi-year products are really essential for the Marine Service. They are used for the ocean state monitoring, and they also used to train real-time applications. And we think that the producers and users need to exchange to better prioritize the next developments. So this is what we plan to do in session 1. The ocean reanalyses are also the only information we have for many areas of the oceans, and they extend in a way the reprocessed observations dataset that we have. So it's important to keep Hello? The old way. So you can't see me maybe, but I have a very nice mic. It's very, but it's working well. No longer, okay, sorry for that. So we need these ocean reanalyses, and we need to keep intercomparing them in a, let's say, a regular way. First, deep, in-depth assessments, but also use them regularly as multi-product is also very useful. So this is something we would like to advertise, to push, to encourage. And we're going to talk about this in session 2. And then the final session, session 3, will be about improving reanalyses and the challenges we have, for instance, extending back in time with a very sparse observation network, adding uncertainty information, for instance, using ensembles, or increasing the resolution, adding more processes, etc. So, of course, this is true for physics reanalysis, but also for biogeochemistry, waves, sea ice. And so we will talk about all these components and see and draw recommendations. Okay, thank you for listening. So I think it's better to use this one. Yeah, okay. So I'm very late. I'm not so late, and it's okay. It's okay. So I think, what is the next step? Can Juntue or Romain tell me? Is there? Yeah. Okay. Sorry. Thank you.
Any questions in the audience here in the room?
I was very clear, but their ears are broken because of the click. Andrea.
Okay.
Thanks, Marie. My question is about the. You mentioned let's say the scheme to go a bit the different streams for real time and delay time. You mentioned the ERA 5 being produced in near real time, but many other observational data sets are delay time mode. I think of altimetry first, but not only. So this will basically, you're planning to have this real time, but then go back after a while and use all the process data set. If you can say more details, would be useful. Thank you.
Thank you. So yes, the strategy we have is that we update regularly, we extend regularly in time, so not to stay too far from real time and to allow for ocean monitoring activities or ocean reporting activities, and to also save time to prepare the next version. And typically the life cycle of a reanalysis would be maybe 3 years. So in a 3-year time, we have prepared a new product that we can disseminate, and then we start the previous one. We stop the previous one. And so, but as you said, we have many challenges to organize this. The feed, this operational chain is quite tricky to organize because we need some observations. So we take ERA 5T, we take the real-time feed of observations that are less quality control and not reprocessed. And there's also a jump in sea level, so of course. But we still think it's worth doing it, so to have a continuous time series. But what did I want to say? So we have this thing. And the other tricky thing we have is that we need to organize with the reprocessing that are done in the thematic assembly centers and that do not have really the same schedule. And this is something we need to talk with the data, with the space agencies that produce the reprocessed L2 and stuff like that. We need to talk with them to see how we can organize this production and this value chain so that we end up with something really meaningful for the users in the end. Yes, I think we can move on. Of course, as I said, all the questions, we will take them on Slido and answer later. So yes, so it's for Valentina now.
Thank you very much. So my name is Valentina Giunta. I'm a product analyst at Mercator Ocean International. And as Marie said, today is mostly about talking about the user needs regarding your analysis data, and also understanding a little bit what kind of applications can be built using this kind of data. So I'm not going to introduce Copernicus Marine Service again. This is just to mention that there is a user feedback process implemented in Copernicus Marine Service. And the idea of this user feedback process is try to collect all the user needs, not only from the users of Copernicus Marine, but also across different user communities, such as from external projects, such as Horizon Europe projects, from advisory committees. So we have implementing what is called the Champion User Advisory Groups, which is a group of 18 independent experts where we talk about user needs and applications as well. Then to collect needs through collaboration with other Copernicus partners, through WICAO as well, and from the policy sector, such as from the regional sea conventions. And of course, through different events, such as this one, such as workshops, trainings, and outreach activities where we talk with the users, we collect the needs. So a little bit about how this user feedback process works. So first, as I said before, we collect all these user needs and feedbacks through different events. Then we introduce all the feedback into a database, and then we perform what we call a technical analysis of the feedback to try to understand where are the main gaps in terms of needs for products, but also for services as well. And then we discuss all these needs internally and try to understand how can we fill those gaps and in the future evolution of Copernicus Marine. And after, if it's possible and feasible, it's going to be implemented and into the service. So as part of our shop, collecting the user needs, we perform a reanalysis service each year, trying to collect the needs regarding reanalysis and multi-year products. So we conducted this survey that it was open during 1 month from the end of June to the end of July. And we ask many different questions to the users. So basically for this survey, we target all the active users in the past year, downloading reanalysis and multi-year products. So we have a good participation of around 351 participants. So you can see here in the maps that they are coming from different countries. And well, we have, of course, a great representation of Europe and Asia as well. They belong to different markets, as you can see here, many from postal services and science and innovation as well. But we have people from the marine and conservation, from event and hazards, and well, from many other different blue markets. They use reanalysis data for many applications, but most of them they're using reanalysis data for ocean process studies, for computing long-term trends, but also for initialization for downstream applications. Sorry, there is I think a problem with the colors on the slide, but hopefully you can see something. So we asked a very interesting question to all the users. What do they think, or how they define what is a consistent reanalysis? And we got many answers. And what we did is we went through all the answers, and we kind of collected the main phrases or repetitive words that they were saying. So for them, a consistent reanalysis is one that is accurate, not only especially, but also temporarily. This means that a consistent reanalysis can basically represent all local processes temporarily and scarcely, and that it can represent also extreme events and long-term trends. It is also closer to observations. That means that a consistent reanalysis needs to fit properly the observations available from very different sources, such as Argos, ADCP, and many others measurements. It is the one that is properly calibrated and validated. This is important because it has to have some consistency, and also it needs to be accurate for the users to use it. It has to have a good spatial resolution, but without compromising the quality of the data. It has to be really well documented. That means that users can be able to go back into the documentation and to understand how these products were built, which measurements were used, all the methodology implementing as well. So that means that the users can control and check how everything was done to compute these products. It has to have a consistent approach. That means that it has to be coherent, again, especially and temporally, and hopefully without no gaps, and without no gaps in terms of temporal and especially also, and that it can represent very long periods. And that means also what they say about temporal continuity, that it has to have temporal continuity. That means that it has to be a long period of time without no gaps in especially and temporally. So when we asked the users why they believe there are the emergency application, the emerging applications for this use of reanalysis data, we of course got like many answers with different kind of application, various specifics. So we divided these applications in different topics just to have an idea of what it can be done with the reanalysis data. So we can see that there were many applications regarding ocean dynamics, climate change, downscaling, trends, coastal adaptation, forecast, and biogeochemistry as well. So there is a very wide range of applications that it can be, where reanalysis data it can be used. So when we ask about what do they need to use reanalysis data or to use it more, we got many different requirements. So the first one, of course, is it has to be accurate, and it has to provide uncertainties as well. So for them, the data has to be reliable and consistent. And also, of course, as always, we got some requests about having better spatial resolution, but not only spatial resolution, also vertical and temporal resolution. This is usually a general request for many of the products. Oh, sorry. Also, we got some feedback regarding that the data has to be easily accessible for downloading, that it has to have a continuity in time, and that maybe will be a good idea to have some additional variables such as weight parameters or more biogeochemical parameters. They mention nutrients, carbon, oxygen. They also mention sea level rise. They mention more trends. And yes, and many other variables as well. Regarding the spatial and temporal resolution, this was widely requested by users. They wanted to have better resolution. When we asked them, well, what kind of spatial resolution will suit you best for your applications? Most of them, they say that a spatial resolution between 1 and 5 kilometers, it should be okay for them. And when we talk about temporal resolutions, they believe that hourly or daily data, it's okay for their applications. So you can see that hourly and daily data is actually a general request for all the different spatial resolutions. But most of them, as you can see here on the top corner of the slide, most of them are quite happy and content with the data that is being offered right now. And of course, they always desire to have more resolution, but again, without compromising the quality and the accuracy of the data. We also asked them what do they believe are the major improvements that it can be done for reanalysis products. And this is okay. So again, spatial resolution, of course, is always something that it can be improved, as well as temporal resolution. but many of them, they think that it can be major improvement on simulations. This means to incorporate more observations and to improve the simulation schemes. And also it will be very valuable for the users to have a comparison of the multiple reanalysis data. Like intercomparison is something that users will benefit a lot from. And this is just to basically to start a little bit of discussion today, to understand what the user needs, what it can be offered, and also to try to see what kind of applications are being built using this data to better serve the users in the future. So what is important, just like a takeaway message from this, is that the definitions of consistent reanalysis by the users usually aligns very well with the general consensus of what we think that is a consistent reanalysis. There is a consistent demand for increased spatial, temporal, and vertical resolutions. There are a significant amount of participants of this survey that they believe that there is not enough guidance or documentation explaining how to use the reanalysis data, the constraints, the limitations, the uncertainties, and accuracies as well. So maybe an enhanced documentation regarding data quality or to provide uncertainties will be a very valuable addition for the users of Copernicus Marine. So yeah, that's it for me. Thank you. I think we have time for a question. Yes, 1 second.
Thanks a lot, Valentina. For the increased spatial resolution, do you think is the request to increase the resolution of the current system or have more downscaled applications which are higher resolution in the coastal region, for example?
That is a very good question, which I didn't mention here, but it's true. So in general, they always ask for higher resolution. That is a general request, but some of them, they say that it's not possible to increase the resolution without compromising the data, maybe to offer some data sets that are in specific points or locations with higher resolution. So it doesn't have to be a global product with very high resolution, but maybe in specific regions or that they can use for other kind of applications. Yeah, well, is there a questions? Okay. I think we can move to the next presentation. So by Tomasz.
Thank you. Hello, everyone. My name is Tomasz Dabrowski. I work with the Marine Institute in Ireland, and I'm going to present examples of the use cases of reanalysis products in my institute. Thank you very much for inviting me to the workshop and giving me an opportunity to talk. There should be more names on this slide than just my name. I'm leading an ocean modeling team, so many people contributed to this presentation. If presentations have to be shared afterwards, I'll have to update this slide. Yep. So just a few words about my institute.
Tomasz, excuse me, can you speak closer to the microphone, please?
Okay.
They don't hear you there.
Is that okay? Is that okay now? Yep.
Yeah,
okay.
Like you can really speak very close.
Sure, okay.
Thank you.
So the Marine Institute was set up in 1991. We are a state agency funded directly by a government department, and we are tasked with undertaking, coordinating, and promoting marine research and development, and to provide related services to ensure research and development in the marine space in Ireland that, in our opinion, will contribute to economic development and create employment and protect marine environment. I work in the section that is an ocean climate and information services section. Largely, we are supporting national and international marine research and development. We operate research vessels. We carry out advanced seabed mapping. We do oceanographic and climate science. We have also information systems and development that disseminate data that we collect and generate. We run a number of observing infrastructures, the likes of Marine Data Buoy Network, National Tide Gauge Network. We also do coastal oceanography, and in Galway Bay, where we are located, we also have an underwater observatory. So I'm responsible for ocean modeling in the Institute. We have a range of different models going from hydrodynamics, which are based on ROMS, and we are also experimenting with the CROCO model these days. We have a wave model based on SWAN, a biogeochemical model, PICES or PISCES, if you like. We call it PICES, but I know many people call it PISCES. And we also have a range of other models, shellfish growth models, oil spill model, number of particle tracking models. These days, we mostly use an open drift model. Downstream services, there is a wide range of downstream services that we provide for the sectors of aquaculture, fisheries, oil pollution, storm surges. We support search and rescue activities as well. We provide services for leisure, for tourism sector, for leisure, like the likes of sailing. We also support policy, MSFD, WFD. We do research on marine litter dispersion, and we also support renewable energy. So now, providing a few concrete examples. Stop working. All the other. Yeah. Okay, thank you. So we use reanalysis products in climate modeling to force the hindcast component of climate models before the models are passed on to climate projections, climate historical analysis and climate projections. This is an example from a, I'm gonna go back to the previous slide. The first example is coming from the, no, that's fine, thanks. Cochrane project, which dealt with harmful algal blooms in a future climate. So in that project, there was a quite complex process. We involved main stakeholders from the very outset of the project. That was very important for developing the actual service. So the modeling component was just a small, it wasn't a small, it was one of the items in the process. But there was also a component dealing with in situ observations on harmful algal blooms. And then the stakeholders were contributing with their knowledge and experience, providing us feedback on possible impacts of what we observed and what we predict. So then both prediction from the models and data from observations were used to establish existing trends and relationships, and then the climate models were used to project what may happen in the future. So the model, we developed a specific model in this project for the southwest of Ireland. That model was of about 1 kilometer resolution, and as part of the work, a hindcast was required in order to prove the model, that the model has a sufficient skill before it's passed to climate simulations. So the hindcast model was forced with the EB multi-year product, the physics. So we took 3D velocity, 3D temperature, salinity, surface height from that model to produce a 20-year hindcast, 1997-2016. Some of the results. So on the left, we have time series going from 1999 to 2016. RMSE is at the top, RMSE for temperature and RMSE for salinity at the bottom. In both cases, we've improved on the EB, which is what we expected and what we wanted, given the high resolution of our model and looking at the specific coastal environment. So in both cases, we reduced RMSE for both temperature and salinity. The TNS diagrams are on the right as well, from our own model and from the EB model. So although our own model predicted slightly colder waters next to the coast, fresher, and the fresher waters were colder. As you can see on the graph, the blue color compared to red one, which is the observations compared to the EB model, but the EB model didn't predict the fresh and cold waters at all. That's due to the resolution of the model, which is 1/12 of a degree, and it didn't quite capture the freshwater plume that we have in the southwest of Ireland. Wrong way again. So as I said, overall, an improvement was observed compared to the EB product, which was what we wanted. And then the southwest of Ireland model was passed on to the actual climate projections. And the first step was to compare historical climate simulation with the presented hindcasts in order to establish whether statistically significant differences existed or not. But I'm going to stop at that, and I'm going to move to the second use case, which is a Sea to Coast project funded under JPI Oceans, JPI Climate. JPI Oceans, JPI Climate, I should say. And it's about, the downscaling climate models onto the Celtic Sea with products and services, mostly for the fisheries and ecosystem assessment sectors or actors. So in this project, the model domain is as presented on the figure. And again, a hindcast run was a component of the development. And in this case, we are doing both physical and biogeochemical projections. So we ran the model, we set up this model as a physics and biogeochemical model. So it was forced with two products, the multi-year physics and multi-year biogeochemistry, both EB products. The methodology involved also bias correction of the EB forcing. So these products were used for initializing the model and for forcing it at the open boundaries. This is a work in progress, and currently the hindcast run is completed. The climate simulations are in progress. Some results for the phytoplankton. On the left, we have time series of diatoms, nanophytoplankton, and both combined into a chlorophyll. Both combined at the bottom figure, and they are compared to the satellite, one of the satellite products. I can't actually say which satellite product it was, but one of the satellite products from the Copernicus service as well. And on the left, it's a climatology. So not looking very good in this case over the Celtic Sea. The comparison between the model that we have and the satellite signal. So this is a work in progress still. Another example of the use of reanalysis is to study marine heat waves. And we did this in the framework of a EuroSea project. Outside of the marine heat waves, we also looked at extreme pH events, or more at long-term trends in pH. And we also looked at dissolved oxygen, low dissolved oxygen events. So for the marine heat waves, we used the classical definition by Hobday et al. 2016. They are the events that are longer than 5 days, and they exceed the 90th percentile of temperature climatology for a given time period. And we did this study for the southwest of Ireland with a view to support the needs of the aquaculture sector. And we based this on the southwest of Ireland model, which was forced by the EB multi-year product. And we looked at the time period 1993 to 2016. So this is the final result. without going into much detail, we found that marine heat waves are to become more frequent, longer in duration, and also more intense. By more intense, we mean the temperature, the departure of the temperature from the 90th percentile is going to be greater. Sorry, not is going to be greater. Over the time period between 1993 and 2016, we've observed those trends. So more frequent marine heat waves, longer and more intense. And then we looked specifically for the aquaculture sector, we looked if there is a connection between the occurrence of marine heat waves and sea lice outbreaks at the farms. So we looked at the time period 1993 and 2016. We got data on sea lice outbreaks from one of the aquaculture operators that we worked with on this project, but we couldn't quite link the outbreaks of marine heat waves with sea lice outbreaks. And we couldn't also find too many trends in sea lice outbreaks as well to relate them to trends in marine heat waves. But in general, salmon farmers advised us that if the trends that we've observed continue, if the events are going to become more frequent and longer in duration and more intense as well, they are concerned because in general it exerts stress on fish, and outbreaks of different diseases, not only sea lice but other diseases may become an issue. We've also looked at deoxygenation events. To define what is a deoxygenation event, we use the same methodology as we used for marine heat waves. So 5 days duration, exceedance of 90th percentile. And we used the oxygen data from the multi-year BGC product. And again, there was no obvious link between the outbreaks of sea lice and the oxygenation events. But what we noticed that some of the deoxygenation events were linked with marine heat waves. But again, maybe the method that we adopted here wasn't really appropriate because although some of the events were defined using this methodology as deoxygenation events, the actual oxygen levels still remained quite high, and they were not of concern to salmon farmers. So maybe for the studies like this, we should look at the actual oxygen concentrations rather than trying to relate them to climatologies. And we also noticed that in some cases, the records were showing lower oxygen levels compared to what we saw in the EB product. And we think that's related to some of the phytoplankton blooms that may not be captured by the models used to generate multi-year products. For example, there are some Carinia outbreaks that cause deoxygenation, and this particular species is not part of the Pisces model, so I suppose it's not fully picked up by the model when they occur. And also, I have a comment here that the reanalysis probably wouldn't capture suboptimal oxygen levels due to the excessive decomposition of organic matter at the actual farms, simply because the model doesn't account for farming, and some of the regions are quite intensively farmed, and local effects due to decomposition of organic matter are of concern, and they wouldn't be represented in the model. We've looked at the pH as well. So we've looked at the seabed pH concentrations to the west of island. So this is the area to the west of island. Island is out of this picture to the east. This is the shelf edge here, Porcupine Bank. Again, for the pH data, we use the EB multi-year product. We've noticed that there are negative trends on the shelf in seabed pH, but there are positive trends in deep ocean. We found the positive trends quite surprising. Maybe it's some artifact in the model. And also based on the results from this, the actual coral reefs are right on the transition zone between negative and positive trends. The coral reefs are mainly located on the slopes, on the shelf slope. So we have a question mark here: how credible are the pH results from this particular product, given the results, negative trends on the shelf and positive trends in the deep ocean? But we've also looked at the small scale oyster farming in Tralee Bay. Again, this is the southwest of Ireland, the same product, the EV multi-year BGC product. Looking at 1993 to 2020, there is a clear downward negative trend in pH. And if this trend was to continue, by 2100, the pH there would be of approximately 7.94. And that becomes a concern to oyster farming. We also generate products for ICES assessments. So some of the questions we are asked were how temperature, chlorophyll, and primary productivity are trending. So again, we used, for ICES assessment, we didn't use regional solutions. We used the global solution, just in case the same analysis is to be carried out by other groups or by ICES themselves for other regions. So for consistency, we use the global reanalysis product to avoid situations whereby some of the regional models would be delivering different results in the overlapping regions and outside of the overlapping regions as well. So I just inserted those two figures. I think they are primary productivity figures, net primary productivity from the global multi-year product, and we are asked to block. This is a monthly. These are monthly averages, and we are asked to block them into five-year averages. So that's what we see on the graph on the left. NPP over a year, 5-year averages, and on the right, I think it's a temperature. It is a temperature. Again, they were asking for 5-year blocks. And this is for one of the ICES regions around Ireland. I think it's 6A. We generated similar products for other boxes around Ireland. Also in Ireland, we have a number of so-called climate action regional offices. One of them, which we work closely with, is on the west of Ireland. And they were asking for specific information regarding the ocean. On the west coast, they selected specific stations, which you can probably see on the map in the top right corner. And they were asking for the likes of temperature and chlorophyll trends and patterns. So again, we used the global multi-year product, physics and biogeochemistry. And on the left, we have chlorophyll, time series, and trends as well. Going back to 1993, I suppose, or to 1990s in a way, all the way to 2020. But what we've noticed here, we looked at the satellite chlorophyll for the same location over the same time period. And whilst we have negative trend in the reanalysis, which is the dashed blue line, at the same time, we have a positive trend in satellite data. So again, there is a question, which product is a credible product, what we get from the satellite or what we get from the reanalysis. Same for surface temperature. One of the locations, doesn't matter so much which location it is. But again, we have temperature time series, and we looked at the trend in them. And what we get from the satellite data is a 4 times greater trend compared to what compared to what we get from the reanalysis product at the very same location. So the last slide. We think that the range of products that are on offer currently, they generally meet the requirements. But one requirement that my colleague passed to me to say here was purely from the forcing our local models perspective. It would be good to have the nanophytoplankton and diatoms separated in the product. We think that the temporal coverage is generally good, but we did have some requests for trends, extending the analysis back to 1980s, 1970s as well. So maybe extension by 1 or 2 decades would be good. Some data sets we think need to undergo better scientific scrutiny. For example, what we've seen in the nearbed pH time series or trends, and also discrepancy between the trends from the satellite and reanalysis. In general, I think I'm sure there is a lot of research going into this as well, but we need to be careful. We need to make sure that global and regional solutions deliver similar information, especially in the overlapping zones. Based on our modeling work that we do for the Celtic Sea, we found that some biases, temperature biases that exist in the EV product for this particular region are actually imported into our Celtic Sea model. So maybe the EV model, I know it's a very specific request, maybe the EV model can be looked at specifically at this issue. And I have the last bullet point is related with developing relationships between chlorophyll and light attenuation, but I can say a few more details about this during the panel discussion. Thank you very much.
Thank you, Tomasz. I don't think that we have, well, maybe we have time for one quick question if there is one in the room. Oh, there is one over.
Thank you. Can you hear me? Well, I'm not sure to understand your point. In fact, I'm here to represent the Ocean Color TAC. Okay, and it seems that you have used some PFT from the Ocean Color products, because I saw a comparison, a blue line and a dark line with diatoms, and I don't remember exactly. Are you using estimation of PFT from Ocean Color TAC?
It's one of the Copernicus products. I don't have the details right now, but it was worked on by my colleague, and I can dig it out. It wasn't one of the PFT. I think it was general chlorophyll. It wasn't a specific functional type. It was general chlorophyll signal.
Okay, just to mention that on this product, there is also an uncertainty estimate which is attached to this product. So I think it would make sense, but it will be part of the discussion, I guess, to, on top of this comparison, to put, well, to display also the uncertainty around the estimation from Ocean Color. Okay, so just a comment.
Sure, yeah. Well, I suppose one thing is discrepancy between what we observe at a given space, location, and time, and the other thing is a trend. So in this particular instance, the climate action regional offices, they were asking for trends. How is chlorophyll trending? So I suppose when the two different products trend different ways, one is negative, one is positive, that's not good. Yeah, sure. Yeah.
Just quick question from Slido related to the marine heat wave. What data did you use as climatology for reference? The same period you have done for the frequency or other data set?
No, it was the same data set. The same data set over the same time period, yeah.
Okay, thank you. Yeah, this is from Slido.
Thank you very much, Tomasz. Now we have a presentation by Tony Candela about, it's a presentation about some applications for biology.
Thank you. So, hi everyone, my name is Tony Candela and I'm talking to you today as an oceanographer, a marine ecosystem modeler and a PhD student in Mercator Ocean International. And today I'm going to present how do we use Reanalysis product in order to understand the juvenile sea turtle behaviors and dispersals at sea. So during this presentation, I will start with a brief introduction to set out the main problematic on our rocks. And then I will present two of our applications in using Reanalysis and aiming to respond to this problematic, which are the modeling of juvenile sea turtle dispersal with our model STAM, and the analysis of real trajectories from satellite tracked sea turtles. And finally, I will end the presentation with showing our needs and suggestions for the futures. Nope. Okay. Not. I'll let you do that. Thank you. So what you need to know about sea turtle is that on our planet, there are 7 species of sea turtle and 6 of them are at least considered as vulnerable against extinction. The last one is not considered as well only because it is data deficient. So we need to protect these species to avoid their extinction. To do so, we need to know where and when they occurs and at all their life stages. And thanks to the recent progress of satellite telemetry, we are able to capture adult sea turtle at sea or on their nesting beaches to put tags on them and to track them in the ocean over varying periods of time. But for the juveniles, it's much more complex. Since they are as small and light as a few centimeters and a few grams, so we cannot put tags on them. And therefore, there is an important gap of information and observation at this life stage, which can last about 20 years and which is commonly named the lost years. So in this context, the first application is the modeling of juvenile sea turtle dispersal during the lost years. So to do so, we used our model STAM for sea turtle active movement model, forced by Global Ocean Reanalysis products. This model aims to simulate the juvenile sea turtle dispersal under the combined effect of ocean currents and habitat-driven swimming activity. So during this period of time, so from the nesting beaches and until the first reproductive migration, we assume that the juveniles only seek to survive, and thus their swimming activity is only triggered by the need to find food and suitable water temperature. So to perform this, our relatively long-term simulation, about 20 years simulations, we used ocean currents, sea temperatures, and proxies for to approximate the prey density for sea turtles, such as the net primary production, for example, from global ocean analyses such as GLORIS 12, WaveRIS, and Cepodim as the forcing fields. This kind of study is really important to know more about this cryptic life stage. You can see here 2 examples of results from STAM. So the first one is the position density control of the dispersal of juveniles from Costa Rica, and the animation of the simulation at the bottom. And this study is really important to allow us to discover new dispersal areas to help in the decision-making process to implement conservation measures on a new dispersal area that we can't see with the satellite tracking of adult sea turtles. The second application is the analysis of real trajectories from the satellite tracking data and interpolating the reanalysis data along the trajectories in order to understand the behavior of sea turtles in relation to their direct environment. So we base our analysis on swimming velocity estimates, assuming that they are specific to the willingness of the sea turtle and that we can determine it by subtracting the current velocity from the total velocity of the sea turtle from the satellite tracked trajectories. So in practice, we apply this method on a passive object, such as drifter, for example, in order to quantify biases and model errors and to get the best estimation of the currents. And then we apply this method on sea turtle trajectories in order to get the swimming velocity estimates and analyze it. Thanks to this swimming velocities estimate, we can focus our investigation on the sea turtle willingness only and highlight some behavioral processes really interesting. So here you have two examples. So on figure A, you can see the seasonal migration processes. So with the willingness of sea turtles to swim north during summer to get more food and to swim south during winter to escape from cold waters. And on figure B, you can see the process of homing behavior. So the homing behavior is the fact that a juvenile sea turtle will stop to forage and develop in foraging areas to go back to the nesting beach to reproduce. And here you can see on blue some random movement from juvenile sea turtles. And then at a given time, a radical change in their heading, swimming heading, to go back to the nesting beaches. So it is quite easy to understand that we need as much improvement as possible in the quality of analysis and to have the less biases in the interpretation of our results. We also want to put an emphasis on surface currents with if possible, I just drink water, please. Thank you. So yeah, put an emphasis of surface currents with, if possible, the production of a coupled analysis with surface currents and waves to better consider the stock drift. We made a few tests about that actually. So on figure A, B, and C, you can see maps of mean velocities from drifters on figure A, from Gloris 12 on figure B, and from reveries, so the stock drift from reveries on figure C. On figure D, you can see the difference of swimming velocity between the drifters and Gloris 12. On figure E, you can see the difference between the velocities from drifters and a combination of Gloris 12 and reveries, so considering the stock drift. And on figure F, you can see the same thing, but with a combination of Gloris 12 and only a fraction of the stock drift as it is calculated in reveries. So you can see here that to consider the stock drift really improve the representation of ocean surface processes and really reduce the biases from Gloris 12 only. And on figure G, H, and I, you can see another example. On figure G, you can see the position density contours from trajectories of drifters dispersing from the Eastern Tropical Pacific Ocean. On figure H, you can see their numerical representation simulated with Gloris 12. And on figure I, you can see the same thing, but simulated with the combination of Gloris 12 and the stock drift from reveries. And here again, you can see the improvement and the benefit to consider the stock drift to represent the surface advection from surface current. We would also need to improve the existing biological variables from low and intermediate trophic levels, and if possible, to generate new variables to better approximate the sea turtle specific diets. So here again, you have some example to illustrate this need. So on figure A and B, you can see in the Southeast Pacific, the position density contour from satellite track adult sea turtle from Costa Rica. And as backgrounds, you can see climatology of net primary production from Sepodim on figure A and a climatology of micronecton density from Cepodium and Fagerby. And also, although the net primary production is largely used in the sea turtle community to approximate the prey density for sea turtles do not feed directly on phytoplankton. They feed on larger organisms and gelatinous organisms such as micronecton and zooplankton. And here, this result confirmed that with proxies like using micronecton is much more consistent with the tracking data. With you see this kind of crescent moon shape in the Southeast Pacific, with high concentration of position from satellite turtle and high concentration of micronecton. So yeah, these are our needs to the futures for reanalysis. And thank you for your attention.
I think we have time for questions. Are there any questions in the room or the other room, maybe? We have one question from Slido. Somebody's asking if there is some publications already on this work.
Yeah, there are some publication on this work. Actually, there are two publications from Lalire and Gaspar and Lalire about the first studies using this model, so STAM. There is also a publication from Gaspar, Candela, me, and George Hillinger from an NGO in the US about a new studies about Razorback turtle in the Caribbean, nesting in the Caribbean areas. And I am writing a paper on the result that you just saw about the Razorback turtle from Costa Rica. And there is another publication in preparation about analyzing the real trajectories with the reanalysis data to investigate this kind of behavioral processes that I just showed.
This way. Okay. The next release of WaveRes will improve the spectral resolution and directionality, and also the grid size of the model, which will be 10 kilometers. It will be good for you to.
Yeah, I think so. But there is always this question about the quantity of the stock drift as it is calculated in WaveRes that we can use to have the best estimation of the currents. As I just show in the presentation, the WaveRes really improved the results, but it's better if we use only small part, some fraction of the WaveRes of the stock drift from WaveRes. So I think we will need some tests, and I will say.
A very quick question. In your experience, can you say something about the temporary resolution that you need for surface currents to have the results that you show? In the sense, maybe also linked to the previous presentation about temporary resolution, hourly, or maybe it's enough less than hourly.
So for the moment, our simulations last about 20 years. So we investigate the general dispersal pattern. So we only use daily means of surface current. But now we are investigating the fact that we have to use the stock drift. And we made some tests with another product that is smoke. And this product also includes the tide currents. And we are making some tests about this kind of question to use maybe hourly resolution for our simulation. But there is always this question about the computational time and which benefit we will have using the hourly data sets. So we have to check that and to see if using the hourly data set will be benefiting us to use that.
Okay, I think there are no more questions.
We have two questions from Slido, but we'll keep in the discussion.
Okay.
So we encourage still participants to give questions on the Slido.
Yes, the link is in the chat for the people online, so they can access the link, the Slido through the link. Thank you, Tony. And now we move to coastal applications. So we have a presentation by Benjamin Bart.
Hello, yes, I'm Benjamin Barton, and I'm going to talk about the coastal applications and limitations of the Scottish Shelfwater Reanalysis Service. And this is work we've done with Michaela and people in the Scottish Government Marine Directive as well. I'm going to start by talking a bit about the Scottish Shelfwater Reanalysis Service, which is one we set up with CMMs. And then talk about the products used to generate this, as well as go on to applications that the general user community have had for this product, as well as our own applications. And then talk a bit about limitations and gaps when using reanalysis of our own, as well as the CMMs products. And then a bit about improvements and expectations for the future. So Scottish Shelfwater Reanalysis Service, I'll just call it SSWRS, uses a 3D FVCOM unstructured model. So it uses a triangular grid, as shown here, sort of where you get the dynamic resolution increasing towards the coast. And using this, we've run a 27-year physical reanalysis of the Northwest European shelf from 1993 to 2019. And this was based on a grid that was previously set up using an earlier version called the Scottish Shelf model. And what we've done is we've taken that grid and improved the atmospheric forcing, the ocean boundaries and river forcing, and then added the daily SST assimilation to make it reanalysis. Yeah, the original grid, so it's got a dynamic resolution that goes from about 10 kilometers at the boundaries offshore in towards about 500 meter resolution at the coastline around Scotland in particular. And this is being delivered by the Marine Scotland Science, which is now the Scottish Marine Directive. So the CMMs products that have been used to set this up. The particular CMMs ones are in bold here, and then we've got some others that aren't CMMs. So for the open boundaries, got this Atlantic European Northwest Ocean Shelf Physics Reanalysis, which comes from Met Office. So this uses a NEMO model. It's actually AMM7, if anyone's familiar with that. And then there's a Baltic Sea Physics Reanalysis as well, covering the same time period. For the atmosphere, we've got ERA5 data. The rivers are Swedish hydrography called EHYPE. And then the tides are harmonic tides from TBX09 Atlas. Then back to the CMMs products on the right hand side, we've got the sea surface temperature simulation. And then underneath that is the validation products that we've used, which are delayed mode surface drifters and Cora in situ observation profiles. So onto the use cases now. So this is more like general what people have been using the model for. So there's been some hydrodynamic downscaling, so some subdomains that have been set up by the Scottish government marine directives. So you can see those are here. There's four of those. I think there's another one planned that really focus on the resolution around Scotland. And then so there's a subdomain of that that's been used here by SEPA, looking at sea lice population density and how that's affected by temperature and salinity and the effect that has on the Scottish salmon farms. And then there's upcoming work looking at potential spatial conservation measures, looking at the connectivity between marine protected areas around the UK, as well as with unprotected sites in Scottish waters. And on the right, sorry, this one here, this is work that Michaela's done using Scottish shelf water to look at the tidal energy extraction and the environmental impact of that. So on the right hand side is the sea surface, the current tidal current speed, just mean tidal current speed, and then on the right hand side is the difference when there are tidal turbines set up to extract power. There's not huge differences, and then future work is sort of starting up looking at a similar thing but using offshore wind energy extraction, so wind farms, and looking at the environmental impact of them. We had a workshop to release the SSWRS product, and during that workshop we asked our users what they use the SSWRS or the Scottish Shelf model for. So it's quite evenly spread between the different options here. Some use it to force smaller regional dynamic models, a small amount for renewable energy applications. The bottom one there's particle tracking for sea lice. That's probably the biggest portion. Then there's particle tracking for other applications, new submodel developments set up, and then input for biological habitat models and adapting and running the Scottish Shelf model for their own requirements. Onto this is what work I've been doing, application of the model data to look at the coastal freshwater around Scotland. So the generally the freshwater gets trapped close to the coast by fronts, and this can affect things like nutrients and larvae and pollutants, how they get dispersed around the coast. So we know it gets trapped, but we want to ask, like, where does the freshwater tend to get retained, and what affects the variability in whether it's dispersed or not. And the Scottish Shelf water is a good tool to use for this because it has the fine coastal resolution, and we've added lots of high resolution river forcing that's internally variable. So on the right-hand side, you can see that there is a mean of the surface temperature and salinity over the full time period. And then below that, we've got the gradient in those two. So that's the gradient in temperature, gradient in salinity. You can see that there is a persistent salinity front around Scotland. And in comparison to AMM7, which is we use to force the boundaries, we don't really find that front. It's a much coarser resolution around the coast. So to understand the variability in whether the freshwater is retained or leaves the Scottish region, I've calculated empirical orthogonal functions to investigate the empirical orthogonal functions on the salinity to investigate where it is at different times. And I look at the first two modes, which make up 45 and 21% of the variability. So on the left is the first mode. If you're not familiar with EOFs, there's sort of two components. There's the time series primary component, And then the spatial map, which so you multiply them together to give you the intensity of the mode within the region. So the first mode has a single pole, so it's showing temporal variability over this sort of time range, where freshwater is entering the domain from the boundaries and rivers. And then the second mode is a dipole, so we've got offshore saline water from the Atlantic that can be drawn onto the shelf, and that sort of in comparison to the freshwater around the coast of Scotland that's sometimes trapped and sometimes released into the Atlantic water. So to really understand what's driving these two modes, I've done some correlations, and the first mode we're looking at now is looking at the correlation. This is the residual current mean. And then I've done correlations with the North Atlantic Oscillation, as well as the mean river forcing within this region that we're interested in. And they both correlate sort of weekly. I've then deconstructed the mean residual current into an Ekman component, a salinity-driven component, a temperature-driven component, and a eustatic surface height with the steric height removed component. So what we see is that this is really a advective diffusion sort of process where freshwater is advected into the domain due to the jet in the front moving the freshwater from the southern boundary around Ireland and the Irish Sea, as well as the river flow, and that's also partly shown in the eustatic height, where there's a volume change from the rivers contributing to that, whereas the Ekman and the temperature is not really contributing here. Then the second mode, which is a little interesting. This has the bipole, as I mentioned before, and is primarily correlated with the rivers on the west side of Scotland. However, it's also primarily sort of wind-driven. So again, I've got the same currents correlated with the salinity primary component here. What we see is the Ekman is really dominating this. So this will be winds from the northwesterly winds, which is pushing water southwestward, and it's meaning that Scotland's acting as a sort of a wedge, I guess, and splitting the water so that on the east side, you've then got water piling up against Scotland. And you can see that in the eustatic height, where there's an increase in the currents on the east side. Whereas on the west side, it's driving water away from the coast, which tends to reduce the eustatic currents, reducing the flow on the west side. And that's what's giving us a pileup of fresh water on the west side of Scotland. And to balance that then, because you've got more inflow on the east, it's drawing in more saline Atlantic water. This is work that's under review at the moment. Final application, just more like a quick advert for my poster later. So I've been looking at particle tracking using the output of the Scottish shelf water model in combination with PyLag to do particle tracking of the larvae between offshore wind and offshore oil rigs. And using those to calculate social network metrics to understand the connectivity between these places. So we've got the degree of how well these places are as a source and how well they are work as a sink. And on the right, this is some validation I've done using a drifter, so that's the black line, and working out how many particles we need to reach full coverage, I guess. So the yellow is 100 particles versus red, which is 4,000 particles. Yeah, so that's just going to be more detail on my poster later. And then onto the gaps and limitations of using the reanalysis. So first, talk about the Scottish shelf water limitations. So the files are like a little bit cumbersome, I guess. They look quite large, and because they're structured, you can't spatially slice them. Then there's the vertical levels, which we've tried playing with a bit, but could do more work. So the deep parts of the domain, we have 20 vertical levels, and so we tried generalized vertical levels, which can have some issues as well. And at the moment, we only run the model up till 2019, so it'd be good to bring it up to the future. And then limitations on the CMM services that we've used to set up the model. It would be, I guess, useful to have river forcing data from CMMs rather than, I guess, we went to the Swedish institute for that. And then it would be good to have hourly data. Oops, sorry, hold on. Okay. Yeah, hourly data to force the boundaries. So we end up using the tidal harmonics, but having a coarse resolution model that's higher temperature resolution would be useful for that. So we wouldn't have to add our own tides, and then more coastal data for validation. Just a quick benefit as well that we during the workshop to release the Scottish shelf water model, Scottish shelf water reanalysis service, we asked our users what they thought the benefits of the Scottish shelf water model were, and generally the biggest answer there is the varied resolution across the domain, followed by the region that it covers around Scotland, and the fact that it's a long-term hindcast now rather than the original one-year climatology. Next-gen reanalysis, well, what we expect, improvements, I guess, for the Scottish shelf water model, and then expectations in general. So the, I guess, accessibility could be improved, perhaps thinking about data formats and improving, perhaps having a way of extracting a time series at a specific point. And developing perhaps tools that would help you do this to set up new subdomains and extract boundary points to do that. Then in terms of perhaps new model runs, adding biogeochemistry, increasing the length of the run up to 2023 would be useful for newer projects. Analysis on the vertical levels to improve that. And then calculating things like climatology of the whole run that we've got now as a replacement for the earlier version of the Scottish shelf model, and downscaling those into the existing domains that we've got, the sub nestings. And I guess for the maybe wider community expectations, improvements to reanalysis could be improving the river forcing in shelf and coastal applications of reanalysis, as well as the coastal resolution, and then coupling with biogeochemistry. So to conclude, Scottish shelf water reanalysis fills its niche, where we apply reanalysis to coastal environments. And we've looked at the applications of sea lice spreading, oil and gas and wind farm larval connectivity, as well as the tidal stream energy extraction. And then my recent work using the Scottish shelf water to analyze the coastal freshwater and look at the salinity fronts and the Rofi around Scotland, and look at the advection and diffusion of the freshwater and the Ekman transport driven mode as well. Next generation could include biogeochemistry and extending the run up to present, and wider improvements could include improving coastal and river forcing. Yeah, that's it for me. Thank you.
I think we have time for some questions. be on the other side. No. Non Slido.
I have a question. So this basically this downscaling that you make, these model outputs are also available for, I saw like in one of the slides that you put, they are available through the Scottish service or something like that. Maybe could you explain a little bit more?
Yeah, so at the moment, I think they are available through the Scottish Shelf Water, the domain that the Marine Directorate of the Scottish Government is hosting them. At the moment, they are only as a climatology using the earlier version, where so the earlier version of the Scottish Shelf model, not the Reanalysis Service, was just run as using climatology forcing, so only run for 1 year. And so that's what those subdomains have been set up to use as well. Yeah, so yeah, it'd be good to generate those with the actual hindcast data that we have now.
Thank you. Other questions? No. Okay. So thank you, Benjamin. And now we are going to hear Anouk Blauw about the application for physical biogeochemical modeling.
Thank you. Can you hear me well? Yeah. Okay, so thank you for this presentation. I've given the opportunity to give this presentation. Yes, no, wrong. Yeah. So I'm here to represent a group of colleagues from Deltares. Deltares is a research and consultancy organization in the Netherlands. We were founded to prevent the Netherlands from flooding, because a large part of the Netherlands is under sea level. So we started with physical models like with water and stones. And now we do mostly numerical modeling, both for our own government, but also for clients worldwide. And we use a lot of CMM's reanalysis products. I asked input from a range of colleagues from mine, physical oceanographer, modelers, and also biochemical modelers. So I wrap everything up together with examples from their work. So I don't know all the details from everything, but I'll give you an overview. So I give some applications in physical modeling with some how we apply them, and also come back with recommendations in the end. So what we experience when using these products. So first, the most often we use CMM's products to estimate the boundary conditions for regional models, so for downscaling. But there's also other applications, such as to add missing variables and processes that are not in our model to complement our own model. We use CMM's current information as a basis for particle tracking modeling. And also when we develop a model in a new area, we first use the CMM's output as a cross-validation for this new model to see if we are getting close. So some examples on boundary conditions. So we use mostly these two global products. And as I said, we have clients in the whole world. So one of the models that I'm personally most involved with is the Northwest Shelf model that you see the area on the screen. But also we did in the Gulf of Maine, in Hong Kong, Mozambique, South China Sea, Durban Coast, South Africa, Arabian Gulf, and many more. The parameters that are mostly used for these physical models are salinity, temperature, and velocity over all depth levels at daily time scale, and water levels at the highest temporal resolution available, so either daily or hourly. And my colleagues said that they are in general happy with the quality, and that they're also particularly happy that in some products the tide and pressure effects are not included, so we can nicely combine them and not get overlaps. So one important modeling application that we have developed in Deltares is the global tide and surge model. You see a zoom in for Southeast Asia there. So you see it's high resolution near the coast and broader resolution offshore. It takes input for temperature, salinity, currents, and in some areas also sea ice. And it is used for making 10-day forecasts, so near real time, reanalyses, and also climate projections. So it's quite intensively used model. Yeah, as I said, it's convenient that pressure effects are not included in GLORIS, and GLORIS is the product that is used as input for this global tide and surge model. This is a 2D model, by the way, this one. And they experienced that for most products, they're happy with the quality, but for sea ice, they still need some improvement, they said. One other nice example is that Deltares joined the Forecasting Floats in Turbulence Challenge. So there a series of floats were released in the ocean in reality and tracked. And then 36 participants tried to project the trajectories of these floats. And Deltares used a combination of products. So the NOAA Global Meteorological Forecast. Not sure if you can see this. And the CMMS product for surface ocean currents. And then our own global tide and surge model. Added them all together, added particle tracking to that. And then in the Delft Fuse software, that is our, say, organization of data flows softwares. It's a flood early warning system. It was originally developed. So you have this cockpit-like screen with all the information. So all these informations were gathered in Fuse. And in the end, Deltares ranked second out of the 31. So looked like these products were good. Another interesting one, I think, is we supported the Dutch sailing team for the Volvo Ocean Race. So we provided information both from the CMMS ocean currents together with the global tide and surge model. And they use that for navigation. Is this a pointer, by the way? This one? This one. So they had the screens in the boats to get all this information and use that for finding the best sailing trajectory. And the interesting thing for us is that the sailing boats also collect physical observations during the sailing that we can use to validate these models. So that's an interesting collaboration. Yeah, they had sensors in the boat, but I don't know more specific details. But I can get you into contact with people if you really want to know. So then we move on to the applications for biogeochemical modeling that I'm more familiar with personally. There we use it also mostly to estimate boundary conditions for downscaled models, and also sometimes as initial conditions for downscaled models, particularly in very large domains where it would take very long to spin up. So these are all the processes and variables in our biological model. So you have the nutrients, nitrate, ammonia, phosphate, silicate. You have 4 species of algae, not species, species groups. So diatoms, flagellates, dinoflagellates, and phaeocystis. Particulate organic matter, benthic grazers, detritus in the sediment, and also dissolved oxygen and total inorganic carbon. So we also have the carbon cycle included in here. And we use that in very many areas. These are some examples. So the Northwestern Shelf model, this one, with a variable resolution. going to the coast, it's 1 kilometer, and here it's more like 8 kilometer, 4 nautical miles. We also used it here in the Gulf of Maine, as particularly in the Massachusetts Bay. And a new one is in the Dutch Caribbean islands. So we have a few here in the north of the Caribbean and a few here in the south. So we have 2 model domains that we force with the CMEMS model. And then we have more variables in our model than are in CMEMS. So we make these translations. Some are very obvious. For ammonia, we have no information, so we assume 0. And here for particulate organic nutrients, we have no information dissolved. So we all derive this from phytoplankton C, which is the only thing that we have for organic matter. But they have not the same temporal dynamics. So it's a bit limited, this approximation. And also we have different groups of algae. So we just assume at the boundaries that it's all dead when it comes in, and then it has to spin up in the model to find its own species composition. One interesting one that I was involved in myself is that we have with the OSPAR working group for ecological modeling, ICG EMO. OSPAR is the policy framework working for all Northwestern Shelf. We have run a modeling ensemble to estimate the historic reference conditions, and those are used for estimating MSFE thresholds for eutrophication. So when is the quality of the ecological status good enough? This is all published in this paper van Leeuwen et al. This year, so if you want to read more details. And we have run these models all with the same forcing conditions as much as possible. And one very key thing is how much nutrients come from land. So I just discussed how much nutrients come from the ocean, but for eutrophication, how much comes from land is very important. There's 2 databases available. One is the ICG EMO database, so that we developed as a group ourselves to get fine resolution information on river loads. And we have for some rivers very good information, daily interpolated many variables, but a lot of the rivers are missing where we didn't have the contacts. And there's another one that is developed by the countries delivering legally obligatory information to OSPAR. So they have to report on how much nutrients they get into the sea. And that is very complete, but it's very limited. It's only total loads per year. So we are now combining these 2, and we have run scenarios with both data sets. They give very different results. And that is an issue. And also for the initial conditions, we used CMEMS data at some point for 2006, and we found that it was way too low compared to the EMODNet observations. So then we replaced these initial conditions from CMEMS with interpolated EMODNet data. And I must admit, I don't know exactly how the CMEMS model is forced, but I have a sneak suspicion that also the river data are not complete. We are struggling with it. Could be that you have already solved it. We would like to know. But this is an important issue, and it adds to what you just said also about river discharge information. It's super important in these areas. One application in the Dutch Caribbean, there we are looking for the influence of the islands on coral degradation through nutrient release from land and from suspended matter from land. So we make a model for total nutrients and total suspended matter, and then we need boundary conditions. And then again, we run into this issue that the total nutrient information is not complete because we only have nitrate and not the total nutrients. So we would really like to have total nutrients and preferably particulate, dissolved, organic, all separate. But I don't want to over-ask, but that would be ideal. And there may be a similar issue with the South American rivers, because if you look here, this is these Dutch islands here. And you see that the South American rivers really have a big influence in this river, in this area. So I don't know how well they are represented in the model, but I think the same issue for that river discharge is important and river loads are important is relevant here, but we haven't checked. So then we come to the overall recommendations, and many have already been mentioned. One is that hourly water levels are not always available from the reanalysis product, and that would be really nice as a forcing for our models. Another remark that was said by two colleagues is that in era 5, you now have a really smooth transition, apparently, between the reanalysis and the forecast data sets. And that would be very nice if it would be the same in CMEMS, because you often use them combined. So that was one wish. One that I also already heard is more information about the model quality, and then particularly in space, like which areas are well represented and which areas are maybe less well represented. And a practical one, a bit more clear error messages when something goes wrong with downloading through opened up. And from the biogeochemical side, yeah, I mentioned it already. We would really like to have more complete information on the total nutrient loads, both from rivers and from the boundaries. And maybe also for suspended matter, although we can maybe also get that from satellite data, but there we also lack it in the Caribbean. So it could be either way or both, but it is a user need from our side. And yeah, an important one is the information on land-based nutrient inputs. So we would like to have the information, and it's also important to have that as good as possible in the models. And for the Northwestern Shelf, we recommend to use this combination of OSPAR RID and ICG EMO datasets, and maybe elaborate further on it and make a new product, CMEMS product. That would be fantastic. So that's all. Thank you for your attention.
So we have time for questions. Is there any questions? Yeah.
Hey, very nice presentation. I was wondering about the river output for nutrients. Is there data out there? Is it completely lacking? Is it unavailable? Or is there a plan to have kind of a global coverage of, what comes out of rivers in terms of nutrients?
I'm not totally aware of what is globally going on. In Deltares, we have these two that I mentioned from OSPAR, and there's also the eHype dataset that was also mentioned by somebody. That is a modeled dataset from a hydrology model. That is, we have seen that in a project was very good, pretty good for hydrology, but for nutrients, yeah. So yeah, it would be nice to have some really good product based on models, observations, smartly interpolated. But as far as I know, it's not yet available. And I don't know what CMEMS models use actually as input. I guess you are also looking for a good available data set.
Yes, perhaps on that point. So actually, Marie mentioned that we will have a talk on day 3 on what is currently done with the GRC in Europe. So in Europe, we have a European flood awareness system called EFAS. So they provide river discharge, but for now it's for emergency and it's focused on the physics. And there will be a presentation by Stefania Grimaldi on day 3 on that. And we are moving forward, trying to do some R&D to also include somehow nutrients in those systems so that we could get nutrients for Europe in EFAS. And otherwise regarding, so it's really research mode for NASA project, European project research. And for the MFCs, just briefly, only, if I'm not mistaken, only the Baltic Sea are using nutrients because they are using heatwaves in their river discharges. Otherwise, they use mostly climatologies.
Yeah, and on top of modeled river loads, I would recommend also making a database with observations just for the validation of the models and as also as information in itself. So I don't know if that is going on. I've heard that there are some EMODnet efforts to make a database of discharges, but not yet for the nutrient concentrations. So that would also be part of that.
Thank you. Is there any other questions?
Thank you. So maybe I've missed it, and if so, I'm sorry, but I didn't quite understood how you are using Copernicus Marine data for temperature, salinity, and currents in addition to GTSM. So are you just combining them to get, for instance, temperature, salinity, do you get steric sea level on top of what you have with the tides and the surges? And for the currents, you are directly using the currents to get in both forecast and reanalysis?
Yeah, now I must admit it is not my work, so I don't know the details. But from what I understood, they take the impact of these variables on the prediction on water levels, because the global tide and surge model predicts water levels for flood forecasting. So they take the information to predict water levels. And I don't know how. But Martin Verlaan, maybe you know him, he is the man behind it and he knows all.
Thank you. And yeah, I think that's it. Thank you. So now we are going to hear Melisa Menedez Garcia, which is online, I think. No. Okay. Do you hear us, Melisa? We can't hear you. 1 second.
We are trying to fix the problem, so because we cannot hear you, but I guess that you can hear us, right? Just 1 minute. Can you speak? Yeah, no, still we have a. Maybe it's your headphones or. No, I think it's the problem is us. Can people online can hear Melisa? Oh, actually, we have the roundtable after. No, so I guess that is, sorry, Melisa, I think it's your mic that is not working. So maybe you remove your headphones or. maybe if, can you check that you have the configuration right for the sound in Zoom? In the audio part. If not, we can make the coffee break now and try to fix the problem in the meantime. Yeah, we have the roundtable after. Okay.
Yeah, Ronan or Julien, do you hear me? If you can try your microphone to check if it is okay from your side.
I can hear.
Yeah, so I guess the problem is from Melisa's side. So if Melisa, you can unplug your...
Can you hear me now? Hello?
Perfect, yes.
Okay, I'm sorry.
Here, no worries.
I think there was some problem in the microphone.
Now you can share your screen.
Okay, I'm sorry for that. Okay.
No worries.
Okay. Can you see the screen again?
Yes, perfect.
And in the presentation way?
Yes.
Okay, so let's go, yeah? Bonsoir, everybody. Good afternoon. This is Melisa Menedez from the Environmental Hydraulic Institute, IH Cantabria. It belongs to University of Cantabria in Santander, Spain. My talk is going to focus on, I will say, historical wave reconstructions, because you will see there are not many wave reanalysis products. Most of them are hindcast. So I'll try to briefly comment about all these topics so quick. First, some kind of introduction to the wave climate variable, mention the available wave data sets, uses and applications of the data set products, how the hindcast reanalysis products are developed, what kind of models we use, validation and correction of the wave reanalysis and hindcast. And then I'll mention the increase of the wave parameters and variables we are reaching in the new reanalysis and hindcast. Some very basic description about the wave climate, wave daily scaling. So briefly, I'm going to talk only about wind-generated waves over the sea ocean surface. They mean all the waves you can see with a period of about 5 to 20 seconds, and they are only generated by the wind blowing over the sea surface. And they are also called gravity waves because the water elevation due to these wind-generated waves tend to the equilibrium only due to the action of gravity. If you can see my mouse, you will see also in the figure that the higher amount of energy of any waves over the ocean, just think on tidal waves, etc., is much more higher for this kind of waves, wind-generated waves. So indeed, I'm not going to mention about all these topics, but waves are very complicated because if you look at the ocean, you will not see always a similar wave height, period, and direction. So waves is the result of wave superposition, and this is because most of the data sets you can get from a wave reanalysis and a wave hindcast products are hourly data, because we integrate all the information of these waves in what we count an hourly sea state. It means in 1 hour, because the superposition and the complexity of all these waves, we are going to get some kind of parameters. And these parameters are mainly wave height, period, and direction. And then we can get hourly time series from the hindcast and products, and as long as possible, of course. So what we would like from this wave reanalysis data and wave hindcast data, we would like to have enough quality, of course, not only mean wave conditions, but also for the extreme wave storms. We would like to get long time series, more than 2 decades is the best. We would like to get high temporal resolution. As I mentioned, we used to manage hourly hydraulic time resolution. We would like to get enough spatial resolution and good distribution from global, regional, local, etc. We would like these data sets to be homogeneous, continuous. We would like to get not only one grid point, we would like to get spatial information because waves change a lot, and especially when we go near shore. We need multivariate data. As I mentioned, at least wave height, period, and duration is very important. And this can be, these general recommendations are for any kind of application we are going to develop with this wave data. Engineering applications, they can be design, maintenance, etc. Coastal management require a lot of wave data information, any climate analysis, but also for the risk assessment for structure offshore, but also for coastal impacts. So in general, yes, I'm showing here some kind of applications and some kind of studies in which wave data is required. They define, of course, the sediment, erosion and sedimentation of the coastal processes, the beach shape. They are also very important for port operability and coastal defenses structure, and they are define the reliability of any structure, a floating offshore structure, a fixed offshore structure, but also the over elevation over sea level we can get due to the waves. So this talk is going to focus on reanalysis and HICAS. I'm going to include both because, as you know, the only difference between reanalysis and HICAS is the assimilation procedures, and there has been indeed nowadays only 2 wave reanalysis products worldwide. The first one has been developed by the European Center, by my colleague Jean-Billot, and it is indeed included in Copernicus system. And the second one has been developed by Copernicus, Mercator in collaboration with Meteo France, by Stefan and colleagues, and it is quite recent in comparison with the previous one. The previous one development by the European Center is called the ERA 5 wave reanalysis. Okay, so this is because we used to manage a lot of wave HICAS at different scales from global to nearshore. This is because it's very important for us also the available information from in situ measurements. I'm thinking on buoy records, and also satellite information. They can provide information mainly from altimetry and scatterometer. Okay, so the only way to get continuous, homogeneous, and long records are the wave reanalysis and HICAS. So how we can develop these data sets, the wave data sets, by running numerical models. The first thing I like to stress is these wave data sets are not included in the ocean and atmospheric models. Even they are not included in the atmosphere-ocean coupled models. So they are independent models that used to be run after getting the outcomes from the wind fields, etc., from the atmospheric models. And all the models nowadays are 3rd generation wave spectral models. They are able to generate and propagate the waves in many different ways depending on the model. And just mention here the most common models you can find. One from the European Center, WaveWave 3 is, I will say, the most common model used at global scale. And then if we go nearshore, we can go to SWAM and others. Okay, so because they are numerical simulations, we need a lot of validation procedures in these models, and showing just here different colors, so a different buoy comparison with wave reanalysis. You can see a scatter plot and quantile plot for each of them, and you can see even if the quality is high, never is going to be similar, exactly perfect. And this is because validation and correction procedures are always required when you are going to use any wave reanalysis and HICAS data. I'm showing here just an example of wave data validation from our global HICAS, the GO2 that we have developed now we are working with the third generation, first with the Era 5 wind fields. On the right, you can see some kind of validation against satellite, the special colors, and if you see the triangles also against worldwide buoys from bias, room mean square error, and correlation. And on the left, on the top, I'm just showing for a buoy in the Mexican Gulf. Red means the Haincas, the buoy significant with height, and black the buoy record under a hurricane condition. And at the bottom, you will see for the global Haincas, only the values, the comparison of the values recorded from buoys at the maximum of the tropical cyclone of the hurricane when they were not broken, and we got the maximum value against the Haincas. So you can see in general, now I will say the skill of the new products, the wave reanalysis and Haincas products is been focusing on the extreme wave conditions. So therefore, not always validation, sometimes we require for any application correction. And because I have introduced waves are complex, we used to correct this data not in a similar way for all kinds of values. We used to correct the data depending on the wave energy, for example, the wave period, and also the direction. And so in this slide on the left, I don't know if you can see my mouse. So the color rose in blue is showing wave condition at a coastal point in when you can see there are two big families, waves coming from west and northeast, yes? So it means maybe the wave reanalysis with Haincas is doing well one of this group and is not going very well one of this group. This is because it's so important to correct the data taking into account the different direction and energy. And we can correct the data if we are lucky, if we can get buoy record. And if not, we have developed also the method can be also applied by using satellite data. And just showing here an example of a correction of the buoy in which we are decreasing the extreme conditions and increasing the low energy waves. So in addition, I like to mention that even in the past, we were managing waves only taking into account the parameters significant wave height and indicator of the wave height. Nowadays, everybody is working at least with wave significant wave height, mean period, and mean wave direction. And because the progress of the technology and the storage size capacity, we have going to more and more information of waves. So nowadays, we used to require for sea and swell wave conditions, these parameters for these two big groups of wave behaviors, but then we are also getting more information about the spectral partitions, then frequency spectrum waves, and finally we are managing three-dimensional wave spectrum. I will see four-dimensional because we are managing the wave energy from different frequencies, directions, and throughout the time. So I'm showing in this picture how very different are the sea and swell wave conditions. So sea conditions used to be very useful for operational applications. Meanwhile, swell conditions are when we can get information about extreme wave conditions. And here I'm just showing an example on coastal areas on the wind, sea, and swell dominance. So you can see most of the coastal areas are light blue. It means we have mixed combination of wind, sea, and swell there. But you can see also there are some areas in which they are swell dominated. And then you can see semi-enclosed seas, bays, etc., in which the dominance inside the harbor, the dominance is the wind sea. And now, if I'm focused on swell conditions, I have to also highlight that we can have not only a specific swell conditions. For example, here in Spain, in the north coast of Spain, when I are swell conditions, we were to be able from northwest. However, in many locations, all the locations you can see with dark blue in this map and green, etc., we have more than one swell family. And this is also very important for many applications to take into account that we have not only one swell behavior, we can have swells with different energy and directions. So in the in the link I'm showing over there, you can show for all the coastal areas. I'm just doing here in this screenshot a zoom of the different swell families we can reach in the Gulf of Lion, close to Toulouse, where I think you are, in which you can see in these locations we have at least in general 3 different swell conditions apart from the sea. I'm not including here the wind sea condition. And you can see the color are the energy. It means the dominated, the high, closer to yellow, the color, the most relevant the family is. But you can see how the directions they are, and the length of the arrow indicate the period. Okay. In addition, we can go to directional information apart from this, and we can get information in which we can see for many, this is just an example for some coastal locations in which we can see just working with the significant wave height, mean period and directions is not enough to understand the behavior of the waves. So I'm not going to give a lot of details, but you can see when we have a split-directional energy, the mean wave direction is not very useful. Now in this plot, I'm changing to wave climate conditions. Here I'm not showing the extreme wave conditions. I'm showing how in usual a maximum significant wave height we regard the mean wave climate conditions. This is because you cannot see dark red in the Atlantic European coast because wave storms there are so common, they are so usual. So I'm showing here when we have very, very unusual extreme conditions from a climate point of view. So you can see the regions in which we have hurricane-induced waves, but also you can see the Mediterranean Sea is almost red dark because sometimes we can have so unusual extreme waves with regards to the mean climate conditions. In this map now, yes, I'm showing the extreme wave conditions by characterizing by the 50-year return period of the significant wave height. And indeed here you can see the regions in which the region in which we can get the most extreme wave conditions at coastal area are the Northern European coast, the Northern Atlantic European coast. So now I'm moving quickly to downscaling because I have so many information, but I have not mentioned the spatial resolution for its data set. So the wave downscaling is so important at regional scale, and it can be done from many different ways, approaches. They can be done by just running numerical models. However, because we need hourly time series, hourly time reconstruction from the case, this is not sometimes very useful. So if we like to get 100 meters spatial resolution and high resolution bathymetry. This is because sometimes there are more and more, and currently because the progress of the intelligence, artificial intelligence, we are getting more and more statistical, what I call statistical techniques in order to get nearshore waves or higher resolution wave products. Sometimes we also can get combination of these products. So now I just mentioned here approach we have developed in order to get waves nearshore from the standard global reanalysis products or global hindcast products, in which we are combining both. We are just selecting a number of cases and running with very high spatial resolution. And before this, we are applying machine learning to characterize all the spatial temporal conditions. And then we apply nonlinear reconstruction functions to get hourly time series with very high resolution. And this is my last slide in which I'm summarizing why we need this wave downscaling data. I'm now thinking on local, from regional to local information, and it could be required for many different applications. I always think on water level estimation because you will see in many coastal areas the contribution to the still water level to sea level of the waves for coastal impacts, flooding, etc. is very, very important. And this can be done by adding what we call wave run-up, setup, and swash. And this can be done by using parametric equations, but also it can be done by using very complex and high computational models, as the example I'm showing in the animation, in which you can see the overtopping due to waves. And then how we need this apart from coastal impacts and coastal flooding. This is also required for many different applications. We used to work a lot with private companies. Most of them are coastal engineering companies, but also port in order to provide port services, climate port services, as I'm showing at the bottom, and also for new renewable energies, which are doing new developments of offshore wind farms. So that's all, thanks. So if you have any questions, I'll be glad to answer. So I think you are, I cannot hear you now.
Now you can hear us, I guess.
Yes.
Perfect. We were asking if there was some questions, so we have here one.
I think you mentioned there were different swell types or categories. I was wondering if you could say what they are.
Yes, so the only way to get different swell systems is getting long time series information from these reanalysis and hindcast, and also getting at least spectral partitions data sets. So once we get this information, we have applied, this is because I saw the URL and the, I hope, next publication. We have been working on categorizing from the directional and frequency point of view, the probability of the different swells occurrence, and we get some kind of families, clusters, in which we can get wave energy, wave period, direction, and wave height associated with different swell systems.
Okay, thank you.
Okay, thank you very much, Melisa, for this presentation. So I guess that we can move to the roundtable. So we invite Andrea, Benjamin, Tomasz, and Anouk to participate. So the idea of this roundtable is to go back to some of the user needs and maybe to explain in more detail what you need for the applications, or to discuss also what are the limitations that you find on reanalysis data currently. So if you want to, maybe if we sit over in the center. I will find another chair. So maybe I can start with one question that we haven't talked about that into too much detail, which is uncertainties. So during your presentation, some of you mentioned some inconsistencies or in the reanalysis data, but do you believe that maybe some uncertainties that can be provided either as a data set or error maps, do you think that it will be beneficial for you to have something like that? I don't know if who would like to add.
Yes, that would be very beneficial, and it is what also my colleagues pointed out. We would like to have some spatial information on certainty, because yeah, if it's good in one location, it's not necessarily also good in another location. But I guess that's also depending on the data availability. So yeah, not in all areas you can show the uncertainty maybe.
Yeah, probably. I think this information in general. Seems to work. Okay. I think this information is in principle available in the reanalysis documentation. Might be not so easy to take for end users. And I think what you pointed out is very important, because it's like regional fitness for purpose of individual products. I'm thinking mostly, for instance, for global products, where you may have different products in overlapping regions, and it could be very useful to just try to see these maps in an organic way to see to guide users which product to use. Yeah.
Yeah, I think it would be useful. I think like maybe there's some sort of standard uncertainties that you can come up with, like some maps or something that everyone just does. I don't know, comparing against like in situ profiles or that sort of thing, and that could then highlight areas that have a better or worse uncertainty.
Definitely very useful, and the simpler it's presented, the better. I have to admit, very often when we use reanalysis products, we don't look too carefully at the quid documents. We just don't have time to analyze every single product in such detail. I was personally involved in the delivery of quids as well for the EB region, biogeochemical reanalysis and analysis as well. At the time, I don't know how it is right now, but at the time, the documents used to have like 100 pages. That's way too long for many users, you know, to review and find the accuracy, you know, or the skill of the uncertainties and quality of the products. So definitely very useful. Spatial maps as well, because some of the regions are so diverse, like EB region. It's important to look at separate regions individually, because the skill may be different in the Celtic Sea from waters around Canary Islands, etc. And yeah, the likes of spatial maps that you mentioned would be very useful. I remember at the time, a few years back, there was a discussion about the traffic light system. Green, high quality product, red isn't quite, orange, somewhere in the middle. But on this front, I don't think there is not a universal traffic light system, because the quality, different users will require different quality of the products as well. So it largely depends on the applications also, in case you are thinking of introducing, or maybe it exists, such a traffic light system. Based on our work with end users, we find that accuracy, uncertainties in the products, the level of accuracy will depend on the users.
Yeah, regarding the quality information documents, so currently there is an ongoing process to improve the way that quality information is being delivered to users. So hopefully this will help the users to understand a little bit more, because information sometimes is there. We understand that sometimes there are long documents, but definitely there is an ongoing work on improving the way that it's being communicated. Also, I noticed that many of you answered that they would like to have only outputs for different kind of application. This is something that agrees with what the participants answer in the survey. I'm just wondering if this outlet resolution is for all variables, for vertical levels, if maybe you want to give more information about what it will be useful.
Yeah, for us, only the water levels to resolve the tides. That is the only one that is requested by my colleagues. So we often have the boundaries very far away, so the resolution will originate within the model normally, but for tides, it's important.
Well, I'm not a user of reanalysis. Maybe I can make the point that I saw from this presentation quite a diverse range of requirements in terms of spatial resolution, temporal resolution, backward extension. So, I mean, obviously, this cannot be achieved simultaneously. So one possible way is to start thinking different streams of production for different user. probably from my point of view, what is missing is the information. I mean, the link between the user requirement that you, Valentina, showed with the actually usage statistics from the Marine Service that could drive a bit better. And then the last point, since we also have non-European reanalysis producer, I think in terms of uncertainty, it could be beneficial. I don't know, might be a bit, there may be practical difficulties, but to increase the catalog of the product, including also, as I said, non-European product that can serve the purpose of improving the uncertainty estimates in an ensemble approach.
So I guess for our use, I think the hourly data I was thinking was for the tidal boundary forcing. So probably specifically sea surface height and currents, U and V as well. I guess would be the main things. And I think what I was thinking was that it may be unfeasible to have hourly resolution at a high spatial resolution just because of the volume of data. So perhaps providing hourly data, but at a coarser resolution that can then be used to force models. If it's further offshore, you don't really need a high spatial resolution.
So at the moment, in Ireland, we managed to nest our models nicely in what is available in reanalysis. We use daily products, and then we add tides separately, but we have multiple nesting. And so we firstly run a regional scale model, and we're actually thinking of maybe decommissioning this regional scale model and focus on coastal scale modeling. And as we do so, we would need higher temporal resolution in the process and spatial as well. So hourly data and increased spatial resolution. Speaking of storm surge modeling, we can pick up tides in 1 hourly products, no problem, but storm surges, we would need even higher frequency, like 10 minutes, so maybe specific transects. Once national institutes or researchers have the modeling systems established, maybe, and those who do storm surge modeling, maybe it's possible to provide them with the likes of 10-minute sea surface height data at specific transects where the boundaries are located.
This discussion is open also to the room. So if someone wants to make a comment or someone has a question. Okay. I guess that we can also talk about one of the user requirements that we found in the survey is about the idea of having a intercomparison between the different reanalysis products. Do you also find this beneficial or for their applications or no in particular?
I mean, perhaps, but I guess maybe all the products have their own specific uses. So maybe if you had a comparison, it wouldn't necessarily tell you that much about what each product is best for.
I'm not sure if I understood the question, Valentina. Could you repeat?
Some of the users during the survey, they found that it would be beneficial for them to have some intercomparison between the different reanalysis products. I was just wondering, is also something that it might be applicable for your work or applications, but
just specifically for Ireland, I suppose yes, because we are in the overlapping zone between EB and Northwest Shelf. So if we had this intercomparison done, at least we would have a choice between the two different models to nest in. That's very specific, I suppose, to where we are.
And also maybe it will be beneficial to talk about a little bit, well, we talk about the temporal resolution. Most of the users, they believe that a resolution between 1 and 5 kilometers will suit most of the applications. Many of you do downscaling, so, and also you need a higher resolution near the coast for coastal studies. What do you think that it will be the ideal resolution, the special resolution that you might need for your application?
Actually, I don't know, but what I hear, because I don't make the grids, so it's not my expertise, but I hear that this the current resolution of this global model is fine. No complaints about that, because we simply adapt. So it doesn't matter.
Yeah, I think the likes of 1 kilometer would do the good job on the shelf. And we are thinking of focusing on coastal modeling. So models just covering coastal waters completely on the shelf. And the likes of 1 kilometer would nicely resolve all oceanographic features which we have on the shelf.
I guess for on the shelf purposes, a kilometer is probably good, but I think the Scottish shelf water one kind of goes high resolution, and then they've got the smaller nestings that I guess try to resolve like very unusual and small scale features in the coastline and sort of sea lochs and things in Scotland. So I think for that, I think high resolution is better.
Well, no, I don't have any particular comment. Just, I mean, it's very difficult to answer, I think, this question. So depending on the application, so it's very useful your survey, and perhaps should be linked also to the specific users. I'm not sure this information was collected, but I think the further step is that the directions that can be targeted.
Yeah, I said it was fine, but I can imagine that if the grid is finer, that we don't need to make such large domains to resolve this downscaling. And also we noticed in the Caribbean, we have a lot of these really small islands. And then, yeah, then for downscaling, maybe it's not a problem, but if you want to use the information directly, then it is no use. It's several islands in one grid cell.
Yes, indeed. I think it's time for the coffee break, and we thank you for your talks and presentation. It is nice to see all the applications developed using reanalysis data. So we will, for the people online, I think we will be back in 20 minutes. And please answer the Slido if you had time, and you can put questions on the Slido as well. So thank you very much.
Allô, Stéphanie, vous m'entendez? Mélanie, do you hear me?
Oui,
Ok.
bonjour.
Ah ouais,
J'ai
le
allumé.
background, il est pas terrible.
Non, il est complètement inversé, puis on dirait
Euh,
que j'ai des trous comme ça dans les... Non, c'est atroce.
alors, de notre côté, c'est une question de luminosité certainement. Et ben, on fera ça en fait. Ok?
Ouais, parce que
C'est pas très
je ne
grave.
sais pas si je dois régler quelque chose sur mon...
Non, je pense que c'est une question de luminosité certainement. Ça arrive de temps en temps. Mais c'est pas très grave.
Ok,
On fera ça.
d'accord. Ok,
Ok?
merci.
Donc, on se donne rendez-vous d'ici 20 minutes.
Oui,
Ok,
je suis là.
super.
Super, merci. À tout à
Ronan,
l'heure.
Ronan, see you in 20 minutes. Perfect. Excellent. Thank you.
Ça va, Ronan?
Salut Mélanie, ça va?
Ça va? Ouais.
Ça va bien.
Ça va être court, hein?
Oui, oui, je voulais
Intervalle.
Alors,
essayer un petit peu.
pour info, on vous entend dans toute la salle.
Ah bon? Pardon. Bon, bah,
À
à plus
plus.
tard, on va se parler sur un autre canal. Merci beaucoup. Ah, merci, ciao.
Ciao.
Yeah, just a few minutes. If participants can come back to their seats, please. Okay. Julien, j'arrête mon partage d'écran. Tu peux partager l'écran.
Que vous voyez bien mon écran? Est-ce que vous pouvez me
Salut,
confirmer que
Julien.
vous voyez bien mon écran?
Oui, salut Julien. Moi, je vois bien ton
Super.
écran, mais pas en mode.
Ouais, parce que j'attendais de vous voir encore. Tac. Là, vous devez le voir en plein écran maintenant.
Voilà, très bien.
Super.
Alors, on attend un peu de temps que les gens se rassient. On est bon.
Okay, so Julien, do you hear me?
Yes.
Yeah, okay, perfect. So thank you, everybody. We are going to hear Julien Le Sommer now. So it's your turn, Julien.
Thank you very much. So I'm indeed Julien Le Sommer. I'm a computational oceanographer working for CNRS in Grenoble, France. And I've been invited to share some thoughts with you today on some emerging usages of ocean reanalysis that may be worth considering for the future. And I've prepared this presentation with my colleague Ronan McAdam, who should be in the room, I believe, right now with you there in Toulouse. So thanks to the organizers for the invitation, and my apologies for not being physically with you there in Toulouse today. So I guess I'd like to maybe first start with the actual purpose of this talk. The question I'd like to address is how ocean reanalysis could be used for improving ocean models and prediction systems. And it's probably true to say that this has long been recognized that there's quite some potential for using information drawn from reanalysis for this purpose. And I'd like to, I guess, draw your attention on the fact that the recent progress in what we may call the field of scientific machine learning are now opening many practical ways how we could turn that into something a bit real. And maybe just to make it clear, what I will call here scientific machine learning is this emerging field at the intersection between numerical methods, machine learning, and computational physics that has emerged over the last 5 years or so. So today I will be reviewing essentially two emerging usages of reanalysis that leverage scientific machine learning, and which I believe are worth considering in shaping the future of CMM's reanalysis efforts. And this concerns in particular the question of the training of machine learning-based prediction systems from reanalysis data, and also the learning of representation of model errors from reanalysis increment. So let's first discuss the improvement of the prediction systems with machine learning. So what you see here is actually a dashboard with some quantitative metrics measuring the quality of ECMWF forecast systems for different lead times and different variables. And the first line shows the results of the high resolution IFS systems. And for each line, you have different data sources. And red means worse than IFS, and blue means better than IFS. So you can see, for instance, here that the ensemble mean forecast generally show best skills, in particular for long lead times. And you can also see that the models are generally more informative than climatology up until lead times of 10 days also. And what I'd like to draw your attention upon is really those three new lines here. So they show the very same metrics, but computed from 3 machine learning based prediction systems that have been initiated with us from the same initial condition as IFS. And I guess the take-home message here is that the most recent machine learning based systems actually show better skill in terms of forecast than the actual IFS high resolution systems. So I guess my point is probably to let you know how they got there in this field. So it all started like 4 years ago when Stefan Rasp, a postdoc in Germany, started formulating a benchmark problem, a case for a machine learning based weather prediction, which he called Weather Bench. And Weather Bench formulates a clear task for machine learning models to achieve, and it also provides like metrics and to measure how well they do. And you put that all together in a GitHub repo with codes and data. And the point I really wanted to make today is that and that's the reason why and how it relates to our discussion today is that the actual training data that came with this problem was the actual ERA 5 reanalysis archive. So that's basically the whole aim of this exercise here, is to use reanalysis data and train prediction systems from this. So I guess you probably see I mean, this was the kickoff, and once the problem got openly released, many like individuals, ML research groups started like really playing with this problem. And those of us who have followed this challenge over the last 2 to 3 years were just very much impressed by how fast the progress has gone in this field. There's now like a full community, many papers coming up. Stefan Rasp is working for Google Research, and Weather Bench is now in its version 2 that has been released like 6 weeks ago, and all the metrics I showed initially actually came from this recent papers. So I guess the point I'm trying to make is pretty obvious here. It's very likely, from my perspective, that people will very soon start using ocean reanalysis for training machine learning based prediction systems, and I think that's something that we as a community should really start and anticipate and consider seriously. Maybe first because this may have like implications for our systems in the future, and we probably need to anticipate those questions. And obviously there are like many open science questions before we can get there. In particular, it's not clear at the moment how the progress on the atmospheric side may translate on the ocean side. For instance, whether ocean reanalysis are a good data set for training ocean prediction system is not clear. We have like different sampling patterns, not that many observations at depth, and probably the relative weights of initialization and model uncertainties are very different. But I guess what I like to advocate is that it's probably for us to actually pave the way for progress in this area. And this means like very practical things, like for instance, document a bit better how well the reanalysis data perform in terms of forecasting tasks, maybe also improve a bit more the way how we represent uncertainties in those systems, but also maybe organize ourselves those benchmark problems for prediction systems. So that's food for thoughts that we wanted to share with you guys here. But this first point may probably have felt like a bit science fiction to many of you in the room. So let's maybe get down to like a more down to earth questions. There are indeed many other like simpler emerging usages of reanalysis data with scientific machine learning that could very usefully be fostered from this community, and this concerns in particular the use of data assimilation increments for improving models. So, as you all know in this room, I guess, reanalysis combines information from physical laws that are encoded in a numerical model, and also information coming from observations. And the way how it works in practice is that we're correcting somehow model trajectories so that it stays close to observation. And it's done by applying what we call analysis increments. And all the game of data assimilation, of the field of data assimilation, is actually to come with clever ideas and algorithms for predicting what should be the optimal increments given the uncertainties in the model and in the observation. And as you can guess, if the model is actually systematically flowed, the increments will always like try and bring back the model towards the trajectory in the same way. And therefore, if the observations are not like too biased, there's a very strong like information content in the analysis increment as to what is the model bias, and therefore as to what are the modeling errors that cumulatively design or build the model bias. So this is something that's illustrated here with information with data coming from a Notion CRS reanalysis system run at GFDL, and what you see is actually CRS concentration. And obviously that's something that's not new. I mean, this has been known for decades, and many clever ways have been proposed for estimating model biases from DA increments, and in particular in the form of state-dependent bias corrections, which somehow are like a representation of model errors. So this is something that is like well established in the field. What I guess is interesting to me is the fact that as many of us in the room may have noticed, there's been quite a renewed attention and interest for those questions in the recent years with scientific machine learning, with several new formulations and algorithms that have been proposed for estimating state-dependent model errors in data assimilation settings. What you can see here, for instance, is an illustration from Farshi et al., where the authors actually introduce an alternating procedure which generalizes the weak constraint for DVAR for training representation of the model error in the form of neural network. And what is important here, I guess, is the fact that this system is actually run online within the data assimilation system, right? So this is really a method that goes deeply into the DA system. And so far, that sort of concepts have mostly been deployed in idealized settings. That makes them a bit like that maybe the next wave, but we're not there yet. But besides those online approaches that are, as I said, probably a bit complicated to deploy in practical cases, people have also started like learning state-dependent biases correction, but in a simpler way, starting directly from the analysis increment. And they are essentially learning this mapping from model state to model errors. And what's interesting here is that they do so only by leveraging the existing DA increments. So that's totally fully external to the system. They're only using the byproduct of the system. So that's why we call those methods like offline methods. They're not like plugged into the systems. And the good news is that over the past 2 to 3 years, there's been like many or several demonstrations that even though offline is theoretically suboptimal versus online, in practical applications, those approaches seems to lead to quite significant improvement in the model climatology and model forecasting skills. So the point I guess I wanted to make here is that it's very likely that in the future we will want more and more to use information coming from reanalysis system, and in particular the increment, for estimating model errors in the future. So that's the second message we wanted to draw your attention upon. So getting to the conclusions and trying to wrap up some maybe recommendations or food for thoughts. I've reported on some emerging opportunities that I think should be considered when shaping the future of ocean reanalysis within CMEMS. And this concerns in particular the question of training prediction systems from reanalysis data and better exploiting the analysis increment. And there are some like key requirements coming from this that we may summarize with, in particular, this need to document a bit better the performance of ocean reanalysis in forecast mode, in particular over quite long lead times, and probably a need to keep improving the representation of uncertainties in ocean reanalysis, as what has been done in the atmosphere may not translate immediately in the ocean. There's also the need to share more systematically the analysis increment as products, and possibly also to provide or think about ways how we could provide the ability to rerun reanalysis system with train error corrections. Once people have started like really getting serious about that game, the ability to plug it back in the system and to assess the performance will be key. And that's something that will be that CMMs will be in a good position to provide. And even more like far-fetched, the question of whether the definition and promotion of those benchmark problems and data challenge falls into the scope of CMMs is something that we could also probably discuss. But that's probably a good way for us to keep moving in an evidence-based, open science and interdisciplinary approach towards like improved reanalysis system. Thanks for your attention.
So thank you, Julien. Is there any questions here? Yeah.
Thank you for your very informative talk about machine learning. So I think analysis increment affected by the observation network. So observation network is changing. The analysis increment, the quality of analysis increment is also changing. Is it okay for machine learning? Do you have any comment about that?
So this, I guess, all what we're talking about here is really like emerging research questions, and most of the published work so far was in the atmosphere with only like a handful of papers with oceanic applications. The question you're raising is a good one. The fact that we have we've had, as we've seen earlier today, quite say a trend in the density of observations, and probably our ability to estimate model error will be stronger over recent years than in the past. And it's probably something, I mean, this change in the density of observations is probably something that will need to be accounted for by any algorithm trying to exploit this information as a byproduct from reanalysis. But that's a good point you're making, indeed.
Thank you. And there is another online questions from Julien Brajard. Ocean time scale is slower than in the atmosphere. Do you think ocean analyses are long enough to train a machine learning based prediction?
Hi, Julien. I think you're probably in a better position to answer this question than I am, but I'd be happy to discuss this. The point you're making is good, though. There's the difference in time scales will have different implications. One is indeed the actual reduction of the amount of useful data. But because the Rossby radius in the ocean is smaller, we also have like more realization of synoptic variability. So my guess would be that the two would compensate. But what may change a lot is probably the fact that on the atmospheric side, you can probably neglect a bit the changes in the forcing over the prediction window, whereas in the ocean, that's not something that we'll need to that we will be able to do. So somehow the forcing will have to be like inputted through the network, and the changes in the forcing will need to be inputted through the network. So there are many subtle changes or differences from the atmospheric case to translate to the ocean case that need to be discussed and addressed. So that's food for discussions, I guess.
Okay, thank you, Julien. So I think it's time to move to the next presentation from Ronan McAdam and Mélanie Juza. Can you hear us? No. Yeah,
I can.
Yeah, sorry. Could you hear me?
Great.
Okay, yeah.
Yes.
Well,
Okay. And could you see my screen?
Could you put your camera on or?
Yes, but you know, I have some trouble with the background.
Okay.
But as you want.
Okay, thank you.
It's a bit rare. Okay, I can
Go
stay like that. Okay, so I'm starting. So good afternoon and thank you very much for inviting us, Ronan and I, to talk about marine heat waves in this workshop. And first, I will talk about what we have learned in the Mediterranean Sea from multi-platform observation and the need of ocean reanalysis for scientific studies and user-oriented application. And then Ronan, so from CMCC, will talk about the role of ocean reanalysis in monitoring and forecasting. So, okay, so quickly, marine heat waves are prolonged periods of extremely warm ocean temperature, and following the commonly used definition of updated 2016, marine heat wave occur when ocean temperature are warmer than the 90th percentile of the climatological distribution during at least 5 consecutive days. And marine heat waves have become more frequent in recent decades worldwide and are expected to be more common, threatening marine ecosystem. Very quickly, marine heat waves are caused by anomalous atmospheric conditions that increase the solar radiation into the ocean and reduce ocean heat losses. And they can also be caused by ocean processes that transport warm water. Marine heat waves have multiple impacts on the physical ocean system, modifying properties and circulation, which in turn may modify nutrient supply, heat and carbon absorption, on marine ecosystem with devastating consequences at the surface and in subsurface, and on the socio-economic system, affecting, for example, sector of the blue economy. The Mediterranean Sea is one of the most vulnerable regions to climate change and responds rapidly to global warming, and its surface warming rate is 2 or 3 times higher than in the global ocean, and show strong spatial variation, as you can see here in the map of sea surface temperature trend estimation over the last 4 decades. So this spatial variability requires specific consideration to understand the drivers, the mechanisms, the consequences of global warming and extreme events on the physical and biogeochemical component of the ocean. So now, the large amount of ocean data from multi-platform observing system unable to characterize marine heat wave in the Mediterranean Sea at local and sub-regional scale, from surface to subsurface, and from open to coastal ocean waters. So first, the satellite observation provide a continuous daily monitoring of sea surface temperature since 1982. They allow the detection of marine heat wave at surface from local to sub-regional scale. Here you have an example of the exceptional marine heat wave detected by satellite in 2022 in the Balearic Sea. And here the reference period used is 1982-2015. The events are characterized in particular by the intensity and duration. So then annual indices are computed, mean and maximum intensity, mean duration, frequency, and total days. And here you have the marine heat wave total days for 2022 in the Mediterranean Sea. And also marine heat wave in the Mediterranean Sea are mainly generated by large-scale anomalous atmospheric conditions. You can see the strong spatial variability of ocean response to extreme events. Then annual marine heat wave indices are computed over all the period from 1982 to 2022 to estimate the long-term changes in marine heat wave characteristics over the last 4 decades. Here you have the map of the trend estimation in marine heat wave total days, and all sub-regions are experiencing increasing trends in all marine heat wave characteristics. And looking at the different the trends in the different marine heat wave characteristics, you can note the important spatial variation again and the different spatial patterns between indices. So the satellite products allow us to estimate the long-term variation of marine heat wave at surface at local and sub-regional scale, but they are limited to the surface and they are less accurate near the coast. So to go further, they have been combined with in-situ observational network. So then, the coastal marine events have been analyzed in the Western Mediterranean Sea over the last decade using both satellite and in-situ data from moorings located in nearshore and coastal waters. The ocean response to extreme events strongly differ from nearshore to open ocean waters, from surface to subsurface, from one site to another site, even in the nearby area. Coastal marine heat wave were observed in many locations with strong spatial and temporal variation in intensity, duration, and frequency. And we demonstrated the importance of high resolution and accurate time series along the coast from moorings to complement satellites. But fixed moorings with limited temporal gaps cover short period and cannot be everywhere along the coast. So last point with observation is now what happened below the surface. After having identified marine heat wave at surface with satellite data, the propagation in subsurface has been analyzed using hydrographic profiles from profiling floats that coincide locally with marine heat wave. And the analysis of the marine heat wave anomaly profile shows the propagation in depth of surface marine heat wave, its strong spatial and sub-regional variability, suggesting the contribution of local processes in the propagation, such as convection, mesoscalade, downwelling, and also the study show the resulting enhanced operation stratification. So in the Mediterranean Sea, the multi-platform observing system has enabled to characterize marine heat wave at local and sub-regional scale and to capture the strong spatial variability and temporal variability, highlighting the role of dynamical processes at local scale and suggesting the diversity of the impact of marine heat wave over the whole basin. So now, why do we need ocean reanalysis for marine heat wave monitoring and understanding? After applying a rigorous model validation, there will be a very useful tool to complement the observing system, in particular in the coastal and deep oceans, to perform long-term change analysis in this area and also process studies that cannot be done with the observing system, to perform OSC and OSSC experiments related to marine heat waves, and to use key derived variable for marine heat waves, such as subsurface temperature or oceanic content, and Ronan will present that in the next talk. Okay, also at SOCIB, we have implemented an open access application to monitor and visualize continuous information on marine heat wave in the Mediterranean Sea at sub-regional scale. This application very quickly enables detection of marine heat wave in real time using satellite observation and with 10-day prediction using model forecasts. And it also provides the monitoring of annual marine heat wave indicators to follow the long-term variation. And this application has been enabled by the Copernicus Marine Service information from observation and modeling systems and has been designed to share timely information understandable to diverse stakeholders. So the last slide to conclude, the results call for the monitoring of marine heat wave from sub-regional to local scale, from surface to subsurface, from open to coastal ocean, using both multi-platform observation and modeling systems. It's important to provide ocean information at sub-regional scale to stakeholders. We need to implement new functionalities in the application, and in particular, extending the information to coastal areas and in subsurface, in particular, using numerical simulation. And finally, it would be very useful to have access to specific model dataset, for example, integrated variable or geographical subset to facilitate the implementation in applications and to reach a wider range of stakeholders at local, national, and regional levels. Thank you very much. And now I give the floor to Ronan.
Thank you, Mélanie. I will need you to stop sharing before I can.
Yeah, I try. Okay.
Well, in the meantime,
Okay.
I can introduce
Yeah, it's
myself.
okay.
Thank you, Mélanie. Thank you for the setup for that great talk. So I'm Ronan McAdam. I work for the CMCC in Bologna, Italy. That's the Euro-Mediterranean Centre on Climate Change. And in the past few years, we've performed a range of studies and activities on marine heat waves. And in each of these, various reanalysis products have played a different role. So today I would like to give you quite a fast and furious tour of how we've used reanalysis to monitor and forecast marine heat waves. And as you can imagine, there's a lot of people involved in such work, not just within the CMCC, but also within the EuroSea project consortium, including Mélanie. So if you remember one thing, it's this slide. These are kind of the main points I want to get across, the various roles of reanalysis in monitoring and forecasting marine heat waves. First of all, as Mélanie alluded to, we need reanalysis to provide that three-dimensional view of marine heat waves. So we need to start looking more at the subsurface in order to fully assess the occurrence and the impacts. Because if you think about the impacts of marine heat waves to aquaculture farms, to conservation efforts, it's very much below the surface where those impacts occur. When it comes to forecasting, reanalysis can provide both baselines to define your climatology and your threshold, but also they can act as a means of validating forecasts. And I will show an example from seasonal forecasting in a few slides. And lastly, and I won't talk about these 2 points, but reanalysis are already used to calculate the oceanic drivers of marine heat waves, mixed layer heat budgets, ocean transports, etc. And we've already had a great talk by Julien on the potential use of reanalysis in machine learning. I would just make the point that I think for extremes, there's perhaps even more desire to see if machine learning can improve the forecast of ocean extremes. I will begin though with a brief description of an intercomparison study we did of marine heat wave statistics in the Mediterranean in a range of products. First of all, we have the satellite-derived Mediterranean specific SST, which is 0.05 degree resolution. We have the high-resolution physical reanalysis of the Mediterranean here at 4 to 5 kilometers resolution. And we also included the GREP, so the relatively lower resolution ensemble of 4 global reanalyses. And what we found that if you look at the basin scale interannual variability and trends for the Mediterranean, you find that there is good agreement between the products. Indeed, there is a bias. So typically our lower resolution products underestimate intensity and overestimate duration. But on the basin scale, we find that the trends were well captured. As you go down to the sub-regional scale to look at the Adriatic or the Aegean, that's when you generally start seeing more disagreement, statistically speaking, between the low resolution products and the high resolution ones. So food for thought going forward. What you use depends on what you do, and I will go forward and use both of these in various ways. First of all, let's look at the subsurface then. So what do we mean by a subsurface marine heat wave? Well, there are various definitions. People take the mixed layer to do mixed layer heat budgets and to understand the drivers of marine heat waves. Here, we're taking a more pragmatic approach. We're taking the ocean heat content of a fixed depth layer. In this case, we're demonstrating with 100 meters because we think that would have a range relevance for various economic and ecological applications. So beyond just looking at the horizontal heterogeneity, we wanted to start looking at the vertical heterogeneity. So on the left, you can see the Mediterranean, the trends in the SST and the ocean heat content, and we've added in the exclusive economic zones. And just quite a simple example here, in 2003, at the surface, we had this very infamous and long-lasting marine heat wave, which at least in the western part of the Mediterranean, had no signal when you consider the subsurface. On the other hand, in 2016, a little known event, but nonetheless, heat waves were registered in the Egyptian waters in 2016. And if you consider the subsurface, it's a longer signal. So the marine heat wave has a different occurrence depending on what indicator you use. That's a simple example, but if you take that a step further, it can be quite clear that we need both indicators, surface and subsurface, to perform a more complete hazard assessment of marine heat waves. Here on the left, we have the maps of mean on the left and trend in the middle for our subsurface marine heat waves for various marine heat wave statistics. And on the right, we have those EEZs split into by surface and subsurface, and we take the top 10. So the countries, the national waters in which the marine heat waves on average last the longest. And of course, the magnitude of the means change, but most importantly, the order changes. So if you want to ask a question, something like which countries are most at risk from longer marine heat waves, well, you can't just use your SST product. You have to rely on also on some indicator of subsurface marine heat waves. And moving on to how we use reanalysis in forecasting studies now. First, very simply, we last year were tracking what is now known as a record-breaking marine heat wave in the summer in the Mediterranean. And we used the 10-day physical forecasting system to look at the SST in the Mediterranean. And because we only have fine gas data for that of up to 2 years, we weren't able, with that data alone, to define a climatology, to define a marine heat wave threshold, which is the 90th percentile. So we took the regional reanalysis system, which I just described, and used that instead, which, depending on your products, you can make the assumption that that is a reasonable baseline to use. In this case, it's the same model setup and architecture. So that allowed us to look at not just the SST, but the marine heat wave occurrence in short-term forecasts. And as you can see from the blue forecast points, it did an exceptional job of that short-term predicting across the Mediterranean. Besides using reanalysis as baselines, we also used reanalysis to validate forecast systems. Here we moved timescale a bit and we look at seasonal forecasts. And some of the major work we were doing recently was to progress the validation of the subsurface ocean in seasonal forecasts, which is something that hadn't been done much before. So we took some of the Copernicus Climate Change Service seasonal forecast systems, and we looked at the surface and subsurface marine heat wave scales. So here we have the number of marine heat wave days in the summer. We use satellite data for the surface and the GREP reanalysis for the subsurface. And I will finish by just showing you how that in 2003, you can see the forecast both at the surface and subsurface really underestimated the number of marine heat wave days that summer. But given that we have a nice long reanalysis to benefit from, we could do a 24-year quantification of the scale in which we found that the subsurface is considerably more predictable for marine heat waves than the surface, which is quite an important point for early warning systems going forward. So I will leave those 5 points there, the key words being subsurface, forecast validation, identifying drivers, and if I can add very briefly, gaps, improvements, and expectations. I do wonder out loud if the validation of extremes could become a standard for the products we produce. And when we eventually want to move on with stakeholder engagement, we will need to have some kind of confidence that we have a consistent reanalysis quality with depth, and we need to communicate that well. And that's all from me. Thank you very much.
Thank you so much. I think we are running out of time for the questions, so we will move to the next presentation from Dillon Amaya.
Hi, everybody. I'm trying to get my video going. Can everybody hear me okay?
Yeah.
Great. Let me share my screen. Okay, can you see my slides now?
Yeah, of course.
Excellent. Okay. Hi, everybody. My name is Dillon Amaya. I'm a physical research scientist at the NOAA Physical Sciences Laboratory in Boulder, Colorado. I work with folks around the United States throughout the National Oceanic and Atmospheric Administration, as well as through different cooperative institutes here in the United States to think about how climate change and variability impacts US coastal waters. And I was asked to just sort of give everybody here a crash course for how NOAA is using ocean reanalyses in their different process understanding studies, but also in our forecasting capabilities as well. So obviously, this is a huge team effort. Here are some of the folks that have worked with me on some of these papers. And specifically, I'm going to be mostly focusing on the United States West Coast and the California current system as we go through some of these results. So let's see if I can progress the slides here. There we go. So I'm going to highlight 3 papers for you today, but because of time constraints, obviously, I'm not going to be able to give you a satisfactory summary of all of these things. I'm just going to sort of highlight a key point from each of the papers and just illustrate for you how we're using high resolution ocean reanalyses in different parts of our products and analyses. So starting with this first paper here on the left, we recently did an evaluation of high resolution reanalyses in the California current system, just to get a sense for how well they perform, how well they don't perform, in what situations they perform better than others, that sort of thing. And high resolution is extremely important in the California current system. It's a very eddy kinetic rich region of the world. Lots of eddies that are very important for modulating upwelling in the region, which is important for modulating the amount of nutrients available for marine ecosystems in this part of the world. Also, the continental shelf of the United States West Coast is very narrow. It's about 20 or 30 kilometers at its widest. So having high resolution ocean reanalyses to interact with that extremely narrow shelf is important to get a correct representation of upwelling in the region as well. So in our comparisons, we looked at GLORY's 12V1, which is, as everybody knows, a 12th degree, ORARS-5, which was the coarsest reanalysis that we compared at 25 kilometers, and then a regional model, actually what we call CCSRA. It's a ROMS data assimilative product that was conducted by the University of California, Santa Cruz, and it's encompasses the United States West Coast as a regional model, and that's at 1/10 degree. So just to give you a sense of the kinds of data sets that we compared to throughout this study, the figure here on the left is just showing you the distribution in shading of Argo floats that have ever been cast in the California current system. The darker blue, the more Argo profiles there have ever been. And then we're also showing the location of different tide gauges, hydrographic sections, underwater glider lines, bottom trawl stations, shore stations for SST and sea level. Just a smattering of in situ observations, basically anything that we could get that was not assimilated into the products, independent checks of how these different reanalyses are doing, so that we could zoom in and see how well they were performing. And just to give you, a very brief highlight of one result, one comparison that we did. This is looking at mean state biases in these three different reanalyses from underwater glider lines. This instrument down here in the bottom right is an underwater glider. We have three continuously running lines that extend from Dana Point, Point Conception, and Monterey Bay in California. These are lines 90, 80, and 66.7, which correspond to the top, middle, and bottom rows here. This is just showing you the temperature, the maximum, or not the maximum, sorry, the total temperature, the mean temperature along each of those lines on the left, and then the bias in each of the models relative to those glider lines. Basically, what you can see, the hashing is a significant bias. You can see that GLORY's overall is doing the best. It has the fewest biases. ORARS-5 has really strong biases in the coastline, and that's related to weakened, not correctly representing upwelling in that part of the world. CCSRA has these strong biases that span the length of the line, and that's because it has a too deep thermocline. And we do similar sort of analyses for other variables and for the glider line temperatures for variability. So this is showing just basically the correlation, point-by-point correlation of subsurface temperature between the model and the observations. And the take-home message here is that all the models actually do fairly well, but GLORY's once again has the highest correlations from month to month with the observations, at least for this time period that we looked at. So I'm going to summarize the whole paper. I realize I showed you one result, but I'm just going to give you sort of the larger overarching conclusions of this paper. And if you're interested, hopefully I pique your interest enough to go check it out. Here's the reference. You can scan this QR code if you want to go see the paper right now. But basically offshore in the California current system, all of the reanalyses perform well, comparable. Near shore, though, the higher resolution of GLORY's and this regional CCSRA reanalysis clearly lead to improvements in the representation of eddy kinetic energy as well as upwelling. And then one important take-home message here is that the best representation of truth in this part of the world, at least, may actually come from reanalyses, because it's a relatively undersampled part of the world. And sometimes we don't have enough observations to stitch together to get a complete story. So often reanalyses can be, more advantageous than just raw observations for a lot of different analyses. So just moving on to this second paper here, this work was trying to understand how well we can forecast coastal sea level in the California current system. And this comes from this idea that forecast skill, at least in the California current system and along the North American West Coast, is often conditional on the physical processes that drive those observations. And along the North American West Coast, INSO teleconnections are very strong, not just through the atmosphere, through the Pacific North American pattern, but also through the ocean, through the propagation of coastally trapped waves that emanate from the equatorial Pacific. And so we were thinking about coastal sea level variability on subseasonal to seasonal timescales, at timescales of 1 day to 60 days, and trying to see how well we can forecast that variability, and specifically if coastally trapped waves can lead to enhanced skill, sort of as a forecast of opportunity. And so this is showing you one such coastally trapped wave from the Glories 12V1. This is an equatorially trapped Kelvin wave associated with the development of the 1997-1998 El Nino. And these shading here is sea surface height anomalies. What you'll see is this equatorially trapped Kelvin wave slams into the South American coastline. Its energy is converted into a coastally trapped wave, and it propagates up the coastline through the Gulf of Mexico, or Gulf of Baja, through Baja California, around the tip of Baja California, and along the U.S. West Coast. So these were just the science questions that we were after for this particular paper. And so as part of that analysis, we need to further verify whether Glories was sort of fit for task, whether we could use it as a tool to verify the forecasts, or if we needed to use in situ measurements at very discrete locations. So what you're seeing here are just a verification of Glories relative to tide gauge stations up and down the North America, or the United States West Coast, where black is the tide gauge and Glories is the nearest Glories grid cell is in red. And these are monthly mean data. The correlation between the two is in the title of each of these. And basically the take home point here is that Glories once again performs extremely well, at least for our purposes here, along the US West Coast. And to our knowledge, none of this data is actually assimilated into the product, just satellite altimetry is. So overall, we were super impressed by how well Glories was doing, and we certainly thought it was fit for task for using it as a verification tool for these products. So as part of this research, we needed to quantify the variability associated with coastally trapped waves as they propagated up the US West Coast. So once again, using the Glories product, we were able to isolate coastally trapped waves moving from the Western equatorial Pacific all the way over, near the Indo-Pacific warm pool, as they propagate along this red path from the west to the east, run into South America, go up the Central American coastline, enter the Gulf of California on the east, exit on the west, wrap up through North America, and cross the Canadian border here on the northwestern side. And so if we trace the path of these coastally trapped waves in Glories, we can absolutely see their propagation across this sort of 25 to 30 kilometer path, all the way from the Western equatorial Pacific to the Gulf of Alaska. So what you're seeing here is a Havmuller diagram that just traces a packet of these waves associated with the development of the 2015-16 El Nino. These are sea surface height anomalies, and they're unfiltered, but we can start to see a more clear coastally trapped wave signal if we apply a wave number filtering and then a time filter as well to sort of capture that subseasonal timescale associated with these Kelvin waves as they go by. But you'll see downwelling Kelvin waves propagate all the way from the Western equatorial Pacific all the way to the Gulf of California, or Gulf of Alaska, over the span of about 120 days. So again, Glories is a super powerful tool to be able to see these things, and we were able to verify these features in tide gauges as well. So again, I can't show you all the results, but I'll just sort of summarize for you what the paper ends up telling us. It tells us that the ECMWF subseasonal to seasonal forecasting model does have dynamical forecast skill of predicting sea level along the California current system on subseasonal to seasonal timescales, particularly in weeks 3 to 7, and generally forecasts initialized with an active coastally trapped wave at initialization. They tend to have a higher skill. So again, you can scan that QR code if you're interested in more details about the paper. And then finally, I just very quickly want to summarize this paper looking at bottom marine heat waves around North America. And this, Ronan and Marie gave a really nice presentation for the Mediterranean Sea, but I wanted to also give you a sense for how we're thinking about marine heat waves in the United States and around North America. Whereas Ronan was looking at subsurface marine heat waves in the upper 100 meters, here we're thinking about marine heat waves specifically at the sea floor along the continental shelf. And the thinking behind that is that there are a series of demersal and benthic marine species, things like snow crab, lobster, Pacific cod. These are critters that live very near or on the seafloor, and they can respond very strongly to bottom temperature variability. For example, Bering Sea snow crab declined by 84% after a 2018 marine heat wave along the bottom of the seafloor in the Bering Sea. Pacific cod declined by 70% after a 2015 heat wave in the California current system. And then in the Northeast US, lobster landings actually increased during a 2012 marine heat wave. So it's not all bad news, but that was also in response to a subsurface bottom marine heat wave. So we're interested in thinking about marine heat waves and how they unfold along continental shelves, along the sea floor. So once again, we turn to GLORIES because it's turning out to be an extremely useful tool for our purposes here, and it tends to be the most accurate thing that we have seen on these sort of small time and spatial scales. And as a part of this project, we also worked to further verify that GLORIES well represented bottom temperature variability around North America. So this figure is just showing you bathymetry in GLORIES down to 400 meters, which we define as the continental shelf. And then each dot is representing an independent bottom temperature measurement that we were able to compare to GLORIES at the nearest grid cell. And this includes moorings. We had different hydrographic sections, also undersea cables. I mean, a smattering of observations that are not assimilated into GLORIES as independent checks of how they're doing. And then again, a similar format to before. Black is showing you the observed near bottom temperature anomaly over which we had a record, and GLORIES is in red for the nearest grid cell. And the correlation is again in the title. And so what you're seeing is overall, all these correlations are certainly significant. Some regions are better represented than others, but given the fact that we're trying to break the reanalysis in some sense, we're trying to zoom into a single grid cell. We were super impressed by how well GLORIES was representing the overall variability in a given region. And we were happy to continue to think about bottom marine heat waves on a larger scale, using that product as a proxy for observations. And just to give you sort of that one quick result about the bottom marine heat waves that we saw in GLORIES, we broke up our analysis into 9 large marine ecosystems that surrounded North America. And these are them here. You're just seeing the bathymetry again down to 400 meters. And that's where we kept our analysis, is just along the continental shelf. Again, you can see in the California current system how thin the continental shelf is, really highlighting the importance of having high resolution data in that part of the world. But here's a result for you. This is showing you the average intensity of a bottom marine heat wave in each of these regions. And just to sort of draw your eye to a couple features, in the California current system, the average intensity of a bottom marine heat wave, in GLORIES at least, is as much as 5 degrees Celsius. In the Gulf of California, it's as much as 7 degrees Celsius, so extremely warm events. These are mostly associated with really strong El Nino conditions. And then you can see that there are clear variations in the strength and intensity of bottom marine heat waves that are tied to bathymetric features. For example, in the Northeast US, we have differences between the mid-Atlantic bight here, as well as the Gulf of Maine. And those are driven mostly by how deep the bottom is relative to the continental shelf. And that's another powerful thing about something like GLORIES, is that we can start to look at variations in this intensity as a function of depth. And so what the shading is showing you here is basically, this is just a 2-dimensional histogram telling you what the average intensity of a bottom marine heat wave is as a function of depth in each. It's going to be in each large marine ecosystem, but this is for the East Bering Sea. And basically it shows you that as you get deeper, bottom marine heat wave intensity tends to get smaller, and that makes sense because the variability is also getting lower. But there are also some really interesting non-linear relationships here. We can zoom in on the California current system, for example, where there are 2 regimes of relationships with depth. For example, if you look at grid cells, north of 35 degrees north, you do get a sort of a linear decrease of intensity with depth. But if you look at the Southern California current system south of 35 degrees north, you get a non-linear relationship where you have a peak intensity at mid depths. And this is super important for fisheries managers, because there are different fishes that live at different depths and need to be managed differently depending on the kinds of intensities that they're experiencing. Okay, so I know I'm way over time. I'm just going to zoom through this, and I'll leave these papers up here if you're interested in learning a little bit more about sort of this whirlwind of information that I've given you here. I also leave my email here. Please feel free to shoot me an email if you have any other questions. I appreciate it. Thank you.
Thank you, Dillon. Maybe we have time for one quick question. Yeah.
Hey, Dillon, nice presentation. I was wondering about the bottom intensified marine heat waves. You said kind of ENSO was in play. Am I to infer that in general, they are driven mostly by wind pattern shifts?
The physical mechanisms that drive bottom marine heat waves are very regionally dependent. For example, in the California current system, the drivers are actually in the Southern California current system are primarily driven by changes in the thermocline depth. So if you push the thermocline down, you push all that cold water off the shelf and you're just replaced with surface waters. And you get huge swings in temperature. And that's mostly why we're getting those 5 and 7 degrees Celsius events, because you get coastally trapped waves associated with El Nino pushing the thermocline down and bathing the seafloor with that surface water. So that's not always wind driven. It really depends on where you're at. Sometimes it's due to internal wave dynamics, basically.
Okay, thank you, Dillon. I think we finished with the presentation for today. We can move to the last part. Maybe Marie, you can handle it.
Thank you. We'll be very quick because I think everybody's tired now, and we'll give some practical information for tonight after. Okay. So you still can share your thoughts. You still can answer the Slido poll if you want to. We have made a summary of what have been the answers so far, but it's going to stay open today, and tonight we'll change for another one. But if you want to answer while we talk, while I talk, but the others, don't hesitate to interrupt. Okay. So the summary. Okay. What did you mean?
No, I guess that is just to point out that we saw today like a wide range of applications using reanalysis data, just to see that also the main requirements changed regarding the application. So, but in general, we can say that temporal and spatial resolution are requested, longer time series, better education about uncertainties as well. We talk about river forcing, nutrient data, and maybe some sea ice improvement in the reanalysis data as well. And I think we have more information about additional variables from the survey also, from Slido. So maybe next slide. Yes.
Oh. This one I can do. This one was what on the rating you gave to the documentation we produced. Well, I think this was meant mostly the documentation from the CMMC reanalyses, but this applies probably. It would be nice to extend this question to reanalyses in general, but at the moment we obtain quite a good rating for the documentation, but it's not perfect. So it means that we need to improve. There is still room for improvement. So it's a 4. Okay. Thank you. We can go next. So we asked people to rank what they thought would be the next improvements, the next to rank by order of interest. The next improvements we could apply to reanalysis. So higher spatial resolution comes first. And longer period coverages is also well, it's in second position, so it's very important also for users. Then higher temporal resolution, higher vertical resolution, and additional variables are coming out in this order. So it's interesting for us to note that higher spatial resolution is still important. Thank you. So among the new variables that were asked for, so you have selected Valentina and Tony, just a few. There are others, so we will compile everything. And so we noted bathymetry, river discharges, current velocity, including Stokes drift, biological and biogeochemical variables. There are some missing low intermediate trophic levels, full spectral wave data, tides, nutrients, and suspended matter. And also we noted a higher temporal resolution in some cases. Yeah. So there is also a question on what do you expect, what expected features of the future digital twin oceans are the most interesting for you? Meaning a cloud-based storage with computing facilities, etc. So we asked them to rank by order of preference. And so the wide range of data sources in a single place has success. Then modeling tools arrive in second. And then processing tools for validation, computing facilities, and processing tools for intercomparison. So I wonder why it's the last one. Maybe they expect us to do the intercomparison. So that's our work still. Okay. Was there another one? Okay. So that was it. Do you have questions or comments or reactions? Not yet. Can we go out?
We do the last two Slido questions. They ask for the wind reanalysis.
Yes. There was also Slido questions. So there was a Slido question on the wind. Why do we not disseminate winds together with the reanalysis products? And so this is not yet the case. This is something we are trying to do. We've been trying to do for some time, but it's not authorized today. We cannot disseminate the atmospheric forcing that goes together. But there are winds in the Marine Service catalog. There is a thematic assembly center that provides reprocessed winds. So it's nice also as a validation tool for your forcings. And very well, it's good to know that there are some winds actually. And also there was a question on why reanalysis products are not stored on hourly basis. This question was related with the fact that tides are, well, we don't see tides if we don't have hourly products, but actually global reanalyses don't have tides yet. The ones we disseminate in the Marine Service, they don't have tides yet. And so I think we disseminate daily and maybe hourly at the surface for GLORIS 12, but I'm not sure. Maybe not, no, not yet. But the reanalysis, the regional reanalysis, for some of them, many of them do have hourly data at the surface because they have more processes, including tides, and it's worth showing, it's worth having this temporal resolution. So it's already the case for some of the reanalyses in near coastal areas. That was all we had. There is a question on, do we plan to provide wave peak period and directional spreading for the different sea states decompositions, swell 1, swell 2, wind wave? So for this, I have no clue. Is it something, do you want?
Some users need directional spreading to reconstruct the wave spectra from the partitions. I think it can be provided by each partitions. It can be an evolution for the future, maybe wave reanalysis. However, for the wave spectrum, it's really depending on, capacity of archiving and providing the data. So yeah, but it can be discussed. We can afford to have wave spectra at a grid resolution of 1 degree, for example, which can cover some area, and users can use it for downscaling, for example, of wave models. There are room of finding, yeah. At least when they have directional wave spectra over the partitions, so they can reconstruct the wave spectrum. I mean, the directional spreading.
Okay, thank you. Do you want to ask the last question to Anouk?
Yes, Anouk, there is a question for you. Could you share your thoughts about the best way to collect nutrient data series to validate numerical models? Will be better a fixed station or Lagrangian data from gliders? Are the nutrient sensors confident nowadays?
Yeah, I made a plea both for providing model data at the boundaries and in my mind, that was simply, I think that information is in the model, but it's not shared. That was my reasoning. And then my other plea was for collecting data in near river mouths, so to quantify the amount of nutrient loads to the coastal waters, and their observations can be done. And yeah, indeed, for nutrient sensors, there are some maintenance issues I've understood, but yeah, maybe if it's close to shore, it can be done. I don't know. But yeah, I think we need both the observations, at least collect the information and make them available, because I know a lot of observations are available, but you cannot find them unless you know the people that have them. So that's not really about observations themselves, but more like data management. And then also develop the models, but that's ongoing, I understand.
Okay, so thank you. A last question, very short one, because I see the faces there.
It's not a question, but can I make a comment? Can I make a comment? There was a survey about what new data sets the users would want, and the respondents said bathymetry. I'm not sure if they meant the actual bathymetry, which is available from EMODNet, for example, if they meant the bathymetry from the reanalysis models. So the bathymetry from the models becomes important to know when we try to nest our own models in Copernicus models. So that we know that, for example, at the open boundaries, the two bathymetric sets match, which becomes important when prescribing fluxes, just to make sure that fluxes are the same. So it's important to know for the modelers what bathymetry was used in the actual Copernicus models. So that would be one data set very useful to local modelers.
I was just wondering if it's not already in the static files. Yes, it is. It is actually available, but not from the viewer. It's available from, you have to connect to the FTP, I think, and then you access static files. And among the static files, there is a bathymetry used by the model. So that's information that is stored, but not very visible. So maybe put that thing more visible. Yeah. Okay, thank you. And so maybe we can just close the online session first and say, see you tomorrow to everybody. There is a session on, we're gonna continue with the evaluation of ocean reanalyses, and it's starting at 9 tomorrow morning. And so see you online. Thank you for your participation online. Bye-bye. Yes.